the Tadabur gabbro-anthracite complex is not a single straightforward complex. It has multiple eruption history associated with magmatism. In other words, it is representing some deformation control igneous intrusions. Recent years, mostly two geochronological work came out, 2011, and another one is He et al. 2016. I didn't write it here. So they are mostly contributing some geochronological ages. They are according to their age. The geochronology is much younger. So this shortcut is our group shortcut. So as we told, the complex is having 3 parts: layered, cystose, and local lensoid pegmatoid gabbro-anthracite patches. So these are some typical, field photograph that was not described by some other workers, prior to our research group. So this is the layering in gabbro and anthracite. There is a cystose. It is pegmatoidal variety, second row, field photograph. This one is the, cystose variety, strongly deformed. And last one, the second row is the occurrence of enclosing contidox, migmatite, granitinites, and all these things, just to give you some idea about the occurrence of gabbro-anthracite bodies. Now, we have prepared a litholog. So, although the entire hill range is too big, only 250 meter, roughly 270 to 320 meter, this is represented by the entire gabbro-anthracite complex, in which layered part is dominant and some other parts is also there, that is cystose and pegmatoidal. Is a litholog. So just we, as a part of the conventional work or conventional taxonomy, we have done some modal mineralogy classification, and we have seen that many rock types within the layered complex itself has been envisaged: anarthosite, anarthositic nodite, gabbroic anarthosite, following the classification scheme of IUGS. So this is petrography. I will want to show that detailing I am not going, but I just want to show you that on our classification basis, we have found out adequate information, adequate documentation for both cumulate from the layered part of cumulate and non-cumulate nature. This is a new finding. Within cumulate, rather we should call it as mesocumulate, and the uppermost part is the non-cumulate, which is relatively fine grained. So these are textural addition in our part, from our side. So this is some petrography. I am not going to details. This is a pegmatoidal gabbro-anthracite, mammoth type of occurrence, grain size. So this is like that, hand specimen. And this is the electron microprobe analyzer, just to give an idea that entire mineralogy or mineral chemistry portion we have carried out.
Kunavaram alkaline complex, or KAC, is emplaced at the contact zone between the Eastern Ghat belt and its adjacent cratons. At the same contact zone, numerous alkaline plutons are emplaced, which are dated between 1.47 to 1.32, and they are correlated with a with a major intercontinental event, which is likely to be a part of breakup of the Columbia supercontinent. Now, for the terms of geology of Kunavaram, it is a linear north-southwest trending pluton emplaced in between the Eastern Ghat belt and the Khammam schist belt. It's a 30 kilometer long and 5 to 10 kilometer wide pluton. Nepheline cyanide is the dominant lithology, and apart from that, carbonatites are present, but they are very minor in amount, especially concentrated in the especially concentrated in the northern and central part of the body. A few younger gabbro and cyanide dikes are also cut by the nepheline cyanide. And nepheline cyanide in Kunavaram is made of two lithofacies, hornblende rich and biotite rich. In Kunavaram, nepheline cyanide, it evolved through multiple batches. Among these batches, one magmatic batch is rich in carbonate and which is giving rise to the calciocarbonatite in Cunavaram. In field evidences, we are getting three types of carbonatites in three forms. One is the first one is the calcite segregation in centimeter scale. Second one is the linear carbonate rich bands in meter scale and some thin dikes. Now coming to their field evidences, small patches, centimeter scale patches are embedded in the nepheline cyanide. At the same time, we are getting some calcite segregations which are mantled by the biotite. It's look like a mimic myrolitic cavity in granite. So these two evidences are suggesting that nepheline cyanide is enabled to fractionate the carbonatite melt and which is forming the calcite segregation, which is further supported by our petrographic studies where we can see biotite or hornblende, both the nepheline cyanide is carrying a calcite as an interstitial space. Interstitial calcites is giving an indication that these are forming at the late stage, and this carbonatite melt is further, this residual carbonatite melt is further segregated and forming the calciocarbonatite. At the same time, this carbonatite melt is flown along the nepheline cyanide magma and they are forming the interbanded structures and they are preserving the flow bands. So in interbanded structure and the flow bands are indicating their co-magmatic origin. These are the from small scale, centimeter scale evidences. A meter scale carbonate rich bands are intruded within the carbonate pore nepheline cyanide and their closer view shows that fragments of nepheline cyanide is embedded within the calciocarbonatite, so which it gives an indication that segregated carbonate melts is carbonated melt is segregated in the deeper part and it is injected within the some semi-solidified nepheline cyanide and which is carrying the and more mingling with the nepheline cyanide. Sometimes they are intruded as a dike and carrying some otoliths of nepheline cyanide. So this one some otolith. The slab photo also shows this carbonatite melt is a defragment the nepheline cyanide in the terms of rock fragments and mineral fragments and flows along it. This is also supported by the petrographic study where we can see that fragments of nepheline cyanides are flown along the carbonatite and this carbonatite also evolved with various pulses. It shows grain size variations. Sometimes there occur also small thin dikes and they are showing a very sharp contact with the nepheline, with their host rock nepheline cyanide. Though they are carrying some fragments, it can be it looks like a thin plutonic dikes. There is a possibility these they are also carrying some phenocrystic apatite. So most probably these calciocarbonatites is segregated at much deeper depth and they are transported to the upper level and they are intruded within the solidified nepheline cyanide and occur as a thin plutonic dikes. Geochemically, all these carbonatites are calciocarbonatite in composition and they are having they are showing a signature of the primary igneous type in carbon oxygen isotope signature. And in geochemical variation diagram, pseudo-ternary diagram shows that there are a close correlation between the carbonatite and nepheline cyanide and they are showing a fractionation trend. At the same time, they are having a coherent correlation with a carbonatite and nepheline cyanide and showing a very strong fractional crystallization trend. In RE diagram, they are showing a very fractionation trend where LRE is over HRE and spider diagram shows spike variations in rubidium, barium, thorium, uranium, niobium, tantalum and they are having a very tight clustering for the HRE. So basically there is a possibility that RE are most all REs as accommodated within the carbonatite in the late phase of crystallization, and whereas they are having very they are having low value of LILE because they are maybe in the nepheline cyanide crystallization in the early stage. So they are, and all the they are accommodated within the biotite, titanite, K-feldspar like this. So here I am trying to make one model. So in the Cunavaram nepheline cyanide, a certain pulses are there which are rich in carbonate, and they are able to separate out, fractionate the small pools of carbonate, which is giving to which is segregated and form small patches within the nepheline cyanide. This is the first one, stage 1. In the second stage, these small pools are segregated and form a large pool and transported to the upper level and interacted with some semi-solidified nepheline cyanide, and they are mingled with in a various stages. And so they are that will be the third stage, and fourth stage. These segregated calciocarbonatite is further transported and interacted and intruded within the solidified nepheline cyanide and emplaced as a dike. So basically all Indian carbonatites are mainly derived from the partial melting of carbonated mantle rock, but this is the one of the rare example where we are getting carbonatite is originated from the fractional crystallization of nepheline cyanide magma. That's all.
Yeah, thank you, Munmun. You were well in time. I think we have some time, and now I invite questions.
Okay, very interesting what you showed. I was just thinking of the fractionation that you're seeing. Usually, when you get carbonatite, it's in association with nephelinite. Usually, the silicate magma is even more silica undersaturated, normally, which coexists with carbonatite. So, nepheline cyanide contains much more silica than a nephelinite. So, it's a little unusual that way. The one thing you mentioned during your talk, looking at the really very nice field photographs, is that you said that it looks as if the carbonatite, what you call the carbonatite veins, are synplutonic. I think something like that you mentioned. Now, I don't know what you mean by look like, but I'm just asking you, is it possible that suppose these are later carbonate material rather than that?
Actually, why I am telling synplutonic dikes, because it is cutting across the what are the two evidences, calcite segregations or injected as a linear bands, they are flown along with the nepheline cyanide. So, and the other thing is cut across the foliation of nepheline cyanide, and it is carrying, and both the cases they are carrying apatite as a phenocryst. So that is my
yeah, but you're saying what you're able to say is that the carbonate vein is later than crystallization of the nepheline bearing rock, right? From the cutting across. And in fact, if the foliated part is the primary foliation, I think you're talking about. So if it is cutting across, then it is later. You're not sure how much later.
No,
you're suggesting that it is because of the final stage of fractional crystallization, it became carbonated. But what if it is later? I'm just asking because just the fact that I don't know. I mean, have you tried or maybe at the next stage you will be trying to model to see whether you can get a comparatively silica-rich magma coexisting with the carbonatite melt. Because as far as I know, silica-rich melts have to be more undersaturated to be able to coexist with the carbonatite. So I'm just saying, because it's what you're seeing is a relative sequence. So whether it's possible to discriminate.
Actually, there is a thing, sir, that nepheline cyanide, there particular some batch of nepheline cyanide magma. So that is only rich in carbonate. Others are not reaching in, and carbonatites are associated with that only. So on that way I am
It's
bringing.
a spatial association
Yes,
you're
sir,
saying.
spatial, yes, sir. Association is very spatial.
Yeah, I'm just saying that maybe you
That
need
may
a
be,
little
sir.
more,
Yes,
some other proxy you'll have to use to try and see if you can discriminate. The possibility still exists, I
yeah,
think.
yes, sir.
But interesting, very intriguing.
Thank you.
Can I ask you, can you go to the rarest plots? So, if I understand you correctly, you said that the nepheline cyanide is derived or has fractionated to beef to the carbonatite, yeah? But then, if it is because of fractionation, there has to be in between, there's a big gap.
Yes, sir.
Okay, so either you have less number of data, one possibility. Otherwise, I would say that this may have partially melted, so that you don't have the variation in between. Just consider that. Okay. Yes. So, but again, the gap is the problem. So it has separated. Okay, that is one possibility. Another thing is that in this multi-element plots, okay, you have this nepheline cyanide, okay, and then many of these things like rubidium, barium, strontium, everything has gone down, and also then the zirconium and hafnium.
We have a very less number of nepheline cyanide samples, through which, so there is also creating a gap. I am not able to fill. So analysis I have less, and for that, here, sir, I just took the average of nepheline cyanide. So that's why it is coming there, and for that, sir, basically is nepheline cyanide is crystallizing fast. So all trace elements are accommodated within the nepheline cyanide. So that's why, sir, that nepheline cyanide has curve has gone up, and these carbonatites. Yes, sir. No, that's why, sir, I'm telling, because all RE are accommodated at the late stage. In my apatite, these carbonatites are carrying apatite, so that most probably these REs are accommodated.
Yeah. That RE has to be there only then.
So good afternoon, everybody. Today I am going to present on magma mixing and translithospheric magmatic plumbing system processes in the end Cretaceous lamprophires from Nirvan alkaline complexes from the Kutch Rift zone. So alkaline magmatism is a key event associated with the Deccan volcanism, and they are mostly restricted within the rift zones, and one of them is mostly the Nirvan, which is located within the Kutch. Now, it's a plutonic, gabbroic plutonic complex in which a number of lamprophire dikes. It's a plutonic, gabbroic plutonic complex in which a number of lamprophire dikes are intruded. Along with it, other rock types are like diorite, leucogabbro, pyroxene-rich gabbros we are finding, and a number of mafic dikes are also there. Now, the earlier works on these lamprophires, like Paul 2018 studied the lamprophires and as well as other rock types, and they suggested they are directly generated from the Deccan volcanisms and basically the rift settings. And along with it, Ray et al. In 2010, they also studied it, and they found a dominancy of the amphiboles, which is specific to the catsutite varieties, and they suggested that they have been derived from an enriched lithospheric mantle source. But the Sen et al. 2006 dated as these lamprophires as to be 67 Ma, And of course, this suggests that the Lamprey-fire magmatism has predated the main Deccan volcanism. Now, as we know that magma mixing is a key magma genetic processes within any volcanism or magmatism, but within the Lamprey-fires, which are porphyritic rocks, the genesis for the magma mixing has been overlooked, as mostly they are considered to be directly derived from the mantle source and have been directly implicit within a short time frame. So recently, Yang et al. 2023, they have suggested that from the Yunnan, southwest China, the Lamprey-fires are derived by mixing between the trachytes as well as the lamproids. Along with it, Zhang et al., by studying the macrocrystal from the Lamprey-fires, they suggested a complex magmatic processes have occurred within the Lamprey-fires from the southern Tibetan plateau. Now, also in 2021, we found such complex magmatic processes within the Lamprey-fires from the Mundwara alkaline complex as well as within the Phenomata alkaline complexes. So we were curious to know whether such magmatic processes are also found within the Nirvan Lamprey-fires or not. So the main objectives of the study were, what were the magmatic differentiation processes within the Nirvan Lamprey-fires, identify the phenocryst, genocryst, as well as the anticryst. I can say that the anticryst are not the genocryst, but they have part of the magma, but not in equilibrium with the host rock. Certainly they would have been formed with the more primitive magma. Now, and also examine whether there was a magma mixing or hybridization, reconstruct the pressure temperature conditions during the crystallization, constrain the various magmatic processes occurring along the emplacement of these Lamprey-fires, and define the magmatic plumbing architecture at the onset of Deccan trap volcanisms in comparison to the Lamprey-fires from the Nirvan area. While doing the petrography, we were find good evidences of disequilibrium textures, as a measure of the crystals were corroded, they shown zoning, and many of them had the sieve textures, which directly suggests that they have a disequilibrium, they have undergone disequilibrium conditions crystallization. Now, the first one shows the olivine, where we have a rounded textures in which the margins have been eroded. Along with it, we have found 4 different kinds of pyroxene, which we have distinct on the basis of major oxides and in situ chemistry, as well as optical zoning, which we have found within the microscopes. The first one is in the D, which we found, we call as P1 type. They show a optical zoning from colorless core to pinkish rim, and they also show oscillatory zonings in some few grains also have been preserved. The second type of clinopyroxenes are P2, which have the green core, and they show pleochrysm from the light green to dark green color and are rimmed by a colorless rim. Along with along with it, the third one is the gray core, where we found pleochrysm from light to dark gray color, as well as they have a colorless rimoid. And along with the fourth one is the unzoned clinopyroxenes, which doesn't show any zoning and are colorless pyroxenes. Along with certain zonings are also found within the amphiboles, and we can see the coexistence of the clinopyroxene and the amphiboles, where they have been corroded and the overgrowth is seen within the microphotographs. Now, we have taken the major oxides of these minerals, and they have correlated it with the global pyroxenes which are found within the Lamprey-fires and have been reported from similar other rock types from the alkaline complexes. And we could see that the zoned clinopyroxenes of the P1 type, they are enriched in Mg, and normally they show a fractionation trend where the core is Mg rich and the rim are enriched in iron, as well as aluminum, titanium gradually increases. But whereas the gray and the green core, they are enriched in the Fe contents and they have a higher sodium content within them, whereas the unzoned clinopyroxenes and the zoned P1 type pyroxenes have a lower Na2O content. And there was a distinction between the gray core as well as the green core, is that the gray cores are more enriched within the titanium, whereas the green cores have a lower titanium content within them. Now, being curious whether there's such zoning patterns have been reported from any of the lamprophires from India or anywhere. So we found that Vilatska and they have reported in 1992 the occurrence of such green pyroxenes within the lamprophires, as well as rock in the 1994 also reported the occurrence of the green pyroxenes, and they suggested they have been formed from the evolved magmas. Now, only major oxides could not serve us the best insights into the processes of the magmatic, so we carried out the in situ trace element analysis of these minerals, and in the trace element pattern we see that the P1 type of clinopyroxenes, they show a normal fractionation trend where we can see the core regions have a low RRE content and it gradually increases with the fractionation, whereas the unzoned P type of clinopyroxenes also show the similar trace RRE pattern. While in the multi-element spider diagram, we could see that the colorless core as well as pinkish rim, they show normal patterns and a gradual fractionation pattern is shown. They show a depletion within the strontium as well as in the hafnium. While the unzoned colorless CPX, they show a slight enrichment within the lead content. So it makes a distinct variety. They have a higher lead content within them. Now, possibility could be there that these pyroxenes are Mg rich and they have a higher chromium content. So possibly these could have been entrained from the mantle xenolith. So we have correlated with the trace element compositions of the CPX from the xenolith, and we could find that there is a difference between these. The xenolith CPX shows a positive strontium as well as the negative value in the zircons, whereas our CPX have a positive zircon anomaly. Similarly, taking up the trace elements of the green core clinopyroxenes, they also show similar patterns, but we could see that they have a higher zircon and hafnium content as well as enriched in niobium and tantalum content, whereas more enriched REE rare earth element pattern diagram is there. So why such zircon and hafnium enrichment is there? So we need to find that. No, so after looking through the literature, we could find that these green core clinopyroxenes could form in 3 ways. One of the main could be that they could be directly entrained from the metasomatic veins within the upper mantle regions, and could be the fragments or the xenocryst from the crustal granulites, and third, they could form through the fractionation of the primary magma and the lower crustal chambers. So after correlating them with the metasomatic veins, we could find that it shows a similar pattern with the metasomatic veins. But we discard this theory, as certainly the metasomatic veins would require a low geothermal gradient to be prevalent within the Deccan region during this time. But obviously the Deccan large igneous province suggests that there was a high geothermal gradient and all the metasomatic veins would have been melted to generate the magma. And so the possibility of this is discarded. Now further, we have taken the CPX from the garnet-bearing granulites as well as pyroxene-rich granulites reported by Desai and all. So we correlated them, and we could find that the granulite CPX have a higher thorium by uranium values, whereas ours have the lower ones, and they show a negative niobium tantalum anomalies, while our CPX have a higher. So this also discard that this could not be the fragments of the xenocryst from the crustal granulites. Okay. Now the similar patterns were found for the gray, only the difference was in the titanium content. Now we have calculated the equilibrium melt with these pyroxenes using the CPX to melt partition coefficient of Ubil 2014, and we could see that the colorless or the P1 type of clinopyroxenes melts are less or from the unevolved ones in the primitive magma. In the deeper regions they would have formed, while the zoned ones, they have a significant lead content within their melts else. And similarly, we take up the green core clinopyroxenes. So which evolved magmas could possibly be there? So we correlated it with the rocks which are present within that, but in the major oxides, we had a difference with all the rock types. And apart from, there was report of a Teffrey phonolytic dikes on that by Moitre around 2003. So, but the data regarding their whole rock as well as mineral compositions was not available. So in that constraint, we correlated it with the Banzada bed phonolite whole rock compositions, and we could see that the melts doesn't correlate with them. So again, what we need to do is that, as earlier I have shown that it was reported that green pyroxenes occur in occurrence with such rocks within the alkaline complexes like tephri-phonetic rocks. So we took tephri-phonolytic hall rock compositions from the global area which occur in the similar tectonic setting, and we see that there are similarity between these rock types. And again, we carried out binary mixing models for the colorless rim portions as how they would have crystallized, and we could find that by a mixing between the primary camptonitic magma as well as tephri-phonolytic magma in a 60:40 ratio, they have formed the rim portions. Now, certainly the mixing would have also created a difference or a deviation within the isotopic characters, but what we find that taking up the whole rock isotopic data of strontium and neodymium values and correlating them with the other rock types, we could find that they show similar characteristics, and certainly suggests that these all have been derived from the same same magma source through differentiation process. And we have calculated the pressure temperature conditions, taking up the Wang et al. 2021 for the thermometry, as well as Putrika and Wang 2021 for the pressure regions. So pink pyroxenes, the colorless core, the P1 type, they crystallize at a greater depth between 20 to 14 kilobar pressures, whereas the rim crystallize within the 14 to 8 kilobar pressures, whereas the unzoned color pyroxenes, they are at very low pressure regions. Similarly, the green cores, they crystallize at a very low pressures, while the colorless rims are showing at a higher because of the compositions, but that should not be. So finally, the model, a cartonic model, where we propose that a magma initially generating the camptonitic magma generated the primary P1 core regions, and again they evolved to generate the rim portions, and in certain time any batch of evolved magmas would have been present of tephrinophonolytic compositions having the green core as well as the gray core compositions, and again a batch of magma would have come up which have entrained the initially zoned pyroxenes, and as well as they have mixed up with these evolved melt components to form the lamprophires. So conclusion, the zoning pattern and textures, distinct clinopyroxene purples, 4 pyroxenes have been identified. The P1 type suggests that the magma have crystallized approximately at 58 kilometers core regions, while the rim at 41 kilometers. The GCPX, GYX have formed at a low pressure depth of 30 to 26 kilometers, and rims would have formed within the 60 to 40 mixing ratio between the tephri-phonolytic magma as well as lamprophoric camptonitic magma. And the unzoned color pyroxene lead anomalies would have been formed either through crustal contamination or they would have been possibly generated from a different source. But we need more clear data to suggest that what was the reason for that. Thank you. Thank you. Yeah.
So this your lead enriched and lead depleted clinopyroxenes, are from the same samples?
Yeah.
Oh, okay. So is there any size control, like all have same sizes or there is some?
No, there are different sizes. We have 3 generations.
Okay. So in that case, if there is 3 generations, maybe their evolution, formation history is anyway different.
Yeah.
Yeah. So if you can see the size control versus the composition, maybe it will have some
Okay.
knowledge about how it has evolved.
Okay.
Yeah.
Okay. We'll wind up here. Thank you, Abhay. Have a nice. Thank you. Thank you. So I now call upon Mahendra Kumar Singh from BHU.
Pointer? No. No, not working. Okay. Very good afternoon to all of you. I am Mahen Kumar Singh from Banaras Hindu University. Today I give a presentation on the topic of petrogenesis and geodynamic interpretation of paleoproterozoic and Neo-Archean sociolitic lamprofire in the Bastar Craton. This is a geological map of Bastar Craton, and my study area is basically lying in the easternmost part of the Bastar Craton, which have very close contact with the Eastern Ghat mobile belt. This is a geological map of my study area, which is Nuapada Lamprotic Field, and these two stark marks shows the occurrences of two different lamprofire body from my study area. This is the first two field photographs showing the occurrences of lamprofire. Our lamprofire is basically very hard and compact, meso to melanocratic in nature. And in head segment, you can see the phenocryst of amphiboles, which are very peculiar for the lamprofire. This is a photomicrograph of lamprofire 1 showing the predominance of pyroxene and amphibole, and feldspar are restricted in the ground mass. This is a petrographical image of lamprofire 2 showing the predominance of amphibole. The feldspar are also restricted in the ground mass, which are very peculiar for the lamprofire. This is a backscattered image of lamprofire 1 showing the presence of euhedral apatite, which shows their magmatic origin. This is a backscattered image from the lamprofire 2 showing the euhedral grain of titanite. We have dated both the apatite and titanite in our study. The pyroxene which are present in both the lamprofire basically augetic in nature for the lamprofire 1 and dapsidic in nature for the lamprofire 2. And in this diagram you can see the lamprofire 1 showing their transitional nature, while the lamprofire 2 belongs showing their calcalkaline affinity, and they in this calcium versus titanium diagram they showing their orogenic character, while the lamprofire 1 showing their transitional nature. The amphibole which are present in our lamprofire are classified as a magnesium hornblende for the lamprofire magnesium hornblende for the lamprofire 2 and the pergasite for the lamprofire 1 with some secondary tremolites also there. They belongs to the calcalkaline lamprofire because they have very low content of titanium. And in our lamprofire 1 we found some mica which are classified as a biotite, and they follow the Minot trend. We have dated our lamprofire apatite for the lamprofire 1 and the titanite for the lamprofire 2, and we found 1.5 billion year age for the lamprofire 1 and 2.5 billion years age for the lamprofire 2. Geochemically, both the lamprofire are subalkaline, and they showing basaltic to basaltic antistatic in nature. They belongs to the calcalkaline to high potassium socionitic character. And in this chondrite normalized RE pattern, you can see the lamprofire 1 showing slightly enrichment in LRE in comparison to HRE, while the lamprofire 2 are highly enriched in LRE. They are showing very similar geochemical signature with the CITZ calcalkaline lamprofire, and both the lamprofire showing almost flat HRE pattern, which indicate their source might be controlled by the garnet. And in this primitive mental normalized diagram, you can see the lamprofire 2 are showing very prominent negative niobium, tantalum, zirconium, hafnium, and titanium anomaly, which are the indicative of subduction related metasomatic enrichment, while the lamprofire 1 showing less prominent negative anomaly of niobium, tantalum, zirconium, hafnium, and titanium. It may indicate their lithospheric component got diluted by the asthenospheric melt. As I earlier said, our lamprofire showing transitional nature, and in this lanthanum pi ytterbium versus niobium by lanthanum diagram, they're coming from the lithospheric lithosphere asthenospheric interaction field, while the lamprofire 2 coming from purely lithospheric interaction, lithospheric mantle, and they shows their subduction related enrichment in comparison to lamprofire 1. In both the lamprofire, we found phlogopite in the source, and we tried to calculate our source, and we found both the lamprophire formed by the mixing of the phlogopite bearing garnet spinel lazulite and isotopic hafnium epsilon negative value shows both the lamprophire are enriched in comparison to Chur, and the enrichment may be related with the subduction related metasomatic processes. And the lamprophire 1 belongs to the anorogenic field, while the lamprophire 2 belongs to the orogenic field. You can see in this triangular diagram. So what are the possible geodynamics involved for the generation of two different type of lamprophire from same locality? This model is suggested by the Satpathy et al. In 2002, which suggested sorry. They suggested during 2.8 to 2.5 billion year, there is a subduction of oceanic plate beneath the eastern part of the Bastar Keton, and they metasomatized the lithospheric mantle. And this metasomatized lithospheric mantle might be the possible source for the generation of the 2.5 billion year lamprophire. And this model suggested by the Ratre et al. In 2010. They suggested during the 1.5 billion year time, the closing of EGMB basin took place, and the Bastar Keton got subducted beneath the EGMB basin. Due to the subduction, extensional tectonics got accelerated in Bastar Keton portion, and there is a creation of the rift. And due to creation of rift, there is a asthenospheric upwelling took place, and they again interact with the previously metasomatized lithospheric mantle, and this metasomatized mantle act as a source for the generation of 1.5 billion year lamprophire. Thank you.
A lot of questions can be asked.
How long it took from subduction?
Yes, sir.
And then you got then dispatch of the source
Yes, sir.
and then melted.
Yes.
Up. Yes, you in your model, you
Yes,
showed
sir.
that there was a subduction.
Yeah.
And then you metasomatized
The subduction,
lithosphere.
due to subduction, lithospheric mantle got metasomatized
Correct.
with the.
Yes, I understood. Do you know the time difference between the subduction and the melt that came out?
For 2.5 billion year lamprophire.
2.5 billion lamprophire. What was the time?
New Archean, sir, it's maybe 2.8 billion year. But neodymium isotope data is disturbed, sir. That is why I'm not including in my work.
In both the cases, you are suggesting subduction.
Yes, sir, because I have found subduction related enrichment processes.
And then gap is almost 1,000 million
Yes,
years.
sir, yes, sir. One is 1.5 and another is 2.5.
So exactly repetition, that repetition of subduction of the same kind. I think.
Yeah. During New Archean subduction, asthenospheric mantle, lithospheric mantle metasomatized, and this lithospheric mantle again melted into 1.5 due to the asthenospheric upwelling, and then this is the.
Because even Ratre model that he suggested for 1.42 mafic dikes.
Yeah, Lakhna dike.
And Lakhna dikes.
Yes.
So that is also younger, much younger to your lamprophire.
Yeah.
1.5 something, and this is 1.4.
Yes.
So I don't know that how it is related. So yeah.
Now you have uranium-lead apatite dips.
Yes, sir.
Now interpretation of uranium-lead apatite is not always straightforward, essentially because a lot of common lead is there in
So
apatite.
we have
How
done
much
the,
common lead you have in your apatite?
0.2, sir. I'm not recall right now, but we have done the common lead correction.
So because these two rocks are spatially associated or far
Yeah,
apart?
very closely
So
associated.
having an age difference of more than 1 billion
1
years,
billion,
then
sir.
so you need to be very careful and
yes, sir.
should confirm
This
with
is the
other
beauty.
geochronological boxes that this stands, the different stands.
Sure, sir.
Okay, I think we'll wind up here. Thank you, Mahendra. So this session comes to a close.
And again, I'll request our director to give the memento to the chairperson, Professor Vishwajit Ghosh and Professor A.P. Pradeep Kumar. Now we will take a group photo. Group photo will be taken in the ramp. So please assemble there. And after that, tea is already arranged in the same place, just outside the room. So again, we will be here. We will start our next session from 4:10. So again, we will start our next session around 4:10. Presentation, that's right. Yeah, please give it.
this is the.
Now we will start our next session, session 4, and the session will be chaired by Professor M.E.A. Mondal and Professor Ashish Dogre. So please take the charge of this session.
So we straightforward, we are late, so we'll start this session. There are 4 papers. First paper is by Dr. Raman. So please.
So good evening, everyone. I thank Professor Chalpatra for inviting me, and it's a good opportunity, and also the initiative by the eminent persons here, Professor Talat Ahmad and Professor Somnath Das Gupta and Rajesh Srivastava, for initiating this forum for metamorphism, magmatism, and metallogeny. So I'm sure this will continue doing good interactions during these 3 days, and also will continue to develop as a good geoscience community. So with this background, just today I'm going to present on the petrogenetic evolution of the denitrites from the East Chitradurga Greenstone Belt, Western Dharwar Ketan, implications on the crustal growth and reworking. So in the morning, Professor Sukanta Day has discussed about the Paleoarchean reworking, and also from the westernmost part of the Dharwar Ketan, but I would be concentrating more on the central part of the Dharwar Ketan. So, and as we see the Earth's history, there are debates about whether it's the plate tectonics or plume tectonics, and also what are the compositional variations and through time. So as we see from the early Archean to late Archean, we find compositional variations. Of course, specific rock types such as comatites and TTG, which are characteristics of the Archean. So early Archean more precisely, and they were absent in the late Archean. And also compositionally we have basalts and comatites form most part of the early Archean, whereas when it comes to the late Archean, we have more of granites and less of these 2 components. So this is how things have changed through time. So, and also the crust formation has got its own ways, this is the time scale, present day crust and to the volume of the content crust that is being formed. And as discussed in the morning by Professor Sukanta Day, so variations, different models about whether it is episodic crustal growth or continuous crustal growth, and what is the content of the volume of the juvenile crustal formation, the amount of reworking. So those things are highly debated, and different people have different models, and I don't want to get into those things, but by and large, it says that it has been established that plate tectonics were the major crust formation process. Beyond that, I don't want to go into details. And there's some characteristics of plate tectonics. That is through time there's a fall in the crustal growth, and also the sedimentary records rocks. They record both this transition. Because we don't get them direct evidences, but we should get those evidences through sedimentary rocks, and those things morning he has demonstrated from the Western Dharwar Ketan, western part. And also the increase in the incompatible elements through time and decrease in the transition elements, which has direct implications on the comatite and basalts. Those things also all together reflects the emergence of plate tectonics from early Archean to the Neo-Archean. And most important part is that whether the subduction plate tectonics were operative, and whether they are same from the beginning, and whether they are different through time. So those things to be looked upon. So in this context, studies on crustal evolution are very important. And important part is that, as we all know, crust is an interface layer between the Earth's solid interior and the surface environment. And also it records the evidence for the origin of life, evolution, and oxygenation of atmosphere. And also it gives information of the past climate, extinctions, and also thermal evolution of the Earth. So studies on crustal evolution gives a lot of information. And also it gives some, shows some of the important elements that are required for our life, and also economically important for the society. And also it acts as a very good processes, crustal studies will help in understanding these weathering processes through time. But with all these things, the important point is that whether the net volume of the content crust is increasing or decreasing with time. This is one of the questions to be addressed. And also, this crust evolution deals with the formation and evolution of the Earth's continents, and past is the key to the present. So this is the essence to study the studies on the crustal evolution. So with this little background, just I wanted to get into the geology of the Darwar Ketan. This is the Darwar Ketan geological map after GSI was Vasundhara project 1994. And as we all know, Darwar Ketan is traditionally divided into the western and eastern Darwar Ketans, whereas the western Darwar Ketan is the oldest part and being hosted by the sedimentary hosted greenstone belts. Means most of these greenstone belts are sediment hosted, and also being peninsular gneiss complex, that is the basement for both the things. Whereas when it comes to the eastern Darwar Ketan, we have the this is relatively younger than the western Darwar Ketan, which is between mostly Neoarchean 2.7 to 2.5, and these greenstone belts are very linear greenstone belts, and also most of these greenstone belts are auriferous. And the granites in terms of the compositionally, these are more potassic granites, whereas here TTG are sodic, and also very limited TTG, they occur as the enclaves. And these granitites also, they are classified, characterized into sanicotites, biotite and two microgranites and hybrid granites. So this is the broader crustal view of the Darwar geology. Then the point is that though people think that Darwar is well studied and well understood, there are certain issues in the Darwar Ketan in terms of whether this classification, what is the boundary between the western Darwar Ketan and eastern Darwar Ketan. So whether it is the Chitradurga shear zone is the boundary, whether there are some other views that this close-packed granite forms the boundary between the western Darwar Ketan and eastern Darwar Ketan. And some others propose this western margin of this Ramagiri, this Kolar also forms the boundary between the western Darwar Ketan and eastern Darwar Ketan. And also apart from this, recently some other proposal has come, that divides Darwar into three components. Keeping western Darwar Ketan as it is, whereas the eastern Darwar Ketan, it is further subdivided into central Darwar province and eastern Darwar province. But this is a matter of debate for various reasons. So the boundary, and the most important part is that whether the central Darwar province still exists or not is a matter of issue. But based on this seismological data, people have basically Kaila's work, classical work of Dr. Kaila, and subsequently Dr. Professor S.S. Roy. So they have established that there are distinct crustal variations between the western Darwar Ketan and eastern Darwar Ketan. So here crustal thickness is around 42 kilometers, whereas towards the eastern Darwar Ketan is consistently 35 kilometers and is very constant. And also this moho between underneath EDC is very flat, whereas the rate is undulated. So and regarding the existing models, tectonic models, so there are again views whether it is plate tectonics or vertical tectonics or horizontal tectonics. It's a matter of debate, and different researchers have provided different models based on their own observations. And apart from that, whether subduction is towards the east or west. So those are some of the issues. So I do not get into those things in details, but for all these things, the central point is the Chitradurga greenstone belt. So that's why I wanted to study. Today I'm going to present our results on the Chitradurga granites from the Chitradurga greenstone belts that forms the eastern margin of the Chitradurga greenstone belt, also marks the boundary between western and eastern Darwar Ketan. So this is the geological map of Chitradurga, and as we discussed earlier in the map, this Darwar Ketan is divided in terms of greenstone sequences, the Sargurs, and followed by the Darwar supergroup, which is further divided into lower Baba Budan group and upper Chitradurga group. So, and this Chitradurga forms the part of this Chitradurga group of Darwar. So it is the type area. So basically it has got three stratigraphic divisions, Vanivilas formation, Hirur formation, and the Ingeldal formation and Hirur formations. And the variations depending on the amount of volcanic rocks, but that's not part of our study. And the basic available ages are around 2,600 million years, given by different people. Trendalet has given RBSR age, whereas Jananda has given this uranium-led zircon age. So slight variation is there between these two ages. So important aspect of this Chitradurga greenstone belt is that on either side we have the granites, and to the west you have the older component basement that forms the PGC, Peninsular Gneiss Complex. People say that the Chitradurga is sitting on this Peninsular Gneiss Complex, this basement. And to the eastern side, you have the Chitradurga shear zone, and that is the continuation of this Bukkapatna granite. So, and there are two intrusive granites are there in between, within the belt. So that shows very clear, distinct intrusive relationship to the volcanics. So these are typical, representative field photographs. This is the PGC from the western part of the belt, and to the eastern, this is from the central part, coarse-grained equigranular granite, and this is from the central part. So that is showing them sharp, means contact between, intrusive contact with, between this greenstone and this granite. And to the eastern part, we have the means this sheared, means that is forms the Chitradurga shear zone and marks the boundary between the west and east. Means the shearing activity is variable. So for proto-melanite to means ultramelanite, means that can be visible here in these two field photographs. So and petrographically also means this to the western part we have this TTG, means being dominated means plagioclase, of course means along with common mineralogy quartz and means showing specific textures and all. But whereas when it comes to the central part, we have the more KFLs for potassic granites to the central part, whereas when it comes to the eastern part, we have the means distinct shearing features, alignment of these minerals along a particular fabric alignment, and also grain size reduction. So and so apart from petrography, means we had done a little bit geochemistry for these rocks so based on the QAB diagram, means we divided them into, means this TTG are class means designated as tonalites and granodiorite, whereas this central granite are means are into central as well as eastern are plotted into the granite field. So in the alumina saturation index diagram of Sham, they are means paraluminous. This eastern are showing the paraluminous nature, whereas to the both means central and eastern granites, means which are potassic, are falling into the metaluminous field. So, apart from this, means the bulk rock means trace and RE systematics. So here RE plots to the left hand side, western, central, and eastern part, and to the right hand side we have the primitive mantle normalized multi-elemental variation diagrams. So it shows that means this western margin granites are showing means no specific no European anomaly, but near flat RE HRE patterns, whereas to the both central and eastern granites have the means negative European anomaly and near flat HRE patterns. Whereas means all are showing the high large ion lithophile elements enrichment as well as the depletion of this HFSC. So all these things are characteristics, and that shows have got implications on the petrogenesis and tectonic setting. So when we plotted means as we discussed, means this TTG, they are more sodic and also metaluminous as shown earlier, and there is no European anomaly. Fractionated RE patterns they are showing. Apart from that, in this Martin's diagram, means lanthanum terbium versus basically this RE to depict the RE fractionation and depth of melting features, means these are the western the TTG, means western margin TTG are showing the means so enrichment means some kind of residual melting of this garnet amphibolite field, whereas this eastern and central part they are showing within the means amphibolite to plagioclase stability fields, and the degree of melting means depth of melting is slightly more deeper, means whereas when this comes to these two components they are shallow melting conditions. So and there is no extent of visible evidence for the crustal contamination between these two things. So we did both means zircon geochronology as well as the titanate geochronology uranium lead. So this is a few samples from the western part, and then 2 from the central part and 3 from the eastern part we have done. So basically all are showing means very clear oscillated zoning, and you had means showing the clear-cut magmatic features, most of them, but few are recrystallized other, means one grain is showing xenocrystic nature, so means which has got some older age, 3273, but by and large they are showing, western part is showing 3200, and this central part are showing 2600 million years, and the eastern part has got variations between 2990 and also 2500 on somewhere. So here no details, sir. It's all magmatic, only granites. So and as I said, means we have done both zircon as well as titanate, not one set, means zircon and titanate uranium lead we have done. So in the western margin, so we have got the means this concordant edges, sir, means 3217 million years we have got for the western margin, and corresponding same sample, corresponding titanate has given 3013 million years. So this is the contrast between these two things, which is very, very important. So means so just we try to depict means what exactly this one, it is giving a relative probability around 3039 to 3040. So here the important part is that means how to differentiate magmatic titanites, whether they are magmatic or not, or metamorphic. So they are clear-cut criteria. The point is that when you analyze both the components, zircons and titanate from the same sample, so titanate should be always younger than the zircon uranium lead ages, and also they should have significantly lower thorium and thorium by uranium, unlike in zircon, where the thorium by uranium ratios are slightly variable, whereas here it's very distinct. But in case of here it is 0.2 for the magmatic, whereas in terms of metamorphic it's 0.8 to 2. And also another component, third point, way to differentiate between these two things is that lower Fe by alumina ratio. So with these things you can clearly differentiate magmatic to metamorphic zircons. So with this, and most important part is that earlier the published data shows that this 3028 to 3030 million years is considered to be the age of the western margin granites. So, but our data means we have got this shows the metamorphic event of, given by the titanite, whereas we have got very good 3200 million years. So that shows that means entirely whatever the age that was given earlier by lead was means it's a really metamorphic age, not the magmatic age. So that has got clear implications on the stratigraphic sequence. So this is the thing. So and one more sample we tried. So that is also giving in the same range, 3206 million years. And titanite here means from the same sample, we have tried the titanite and it is giving 2500 million years. So based on this, so we could depict that from the western margin, we have, 4 minutes. So 3200, okay. Magmatic age is 3200, metamorphic 3030 million years, 2 metamorphic events. So then this implications implies that once the source for Darwin supergroup is this TTG, and this marks the upper limit of the Baba group, not the Chitra group, which was depicted earlier. So same the case with central Darwin Keton, with central granites, there is not much variation. So everything is falling within the range. So in fact, this marks the beginning of the Chitra Keton, like as mentioned earlier, unlike mentioned earlier. So in the eastern Darwin Keton, we have got this Bukkapatna granite, is a continuation, means earlier age was 2.98, that same age we have got. And the point is that this Chitraduga eastern margin people didn't thought that it is the, there is no clear-cut evidence, though means people say that shearing has happened, the shear zone that marks the boundary. There is no shearing, the timing of deformation or shearing not clearly defined. So based on structural data, there was some model, but we have got, means apart from this, we have got this event, means, and for this, this reflects the regional synkinematic event. So by putting together means, I don't want to get into that. Basically what I wanted to say is that means between together two geochronometers together will help in understand the things to differentiate the both magmatic and metamorphic history. So then apart from that means we had did some neodymium isotopic systematics, whereas the means western Darwin. So I will go straight to the bottom. Means here we compile the means published data from the Darwin, means available data, and our data means 3.2 is somewhere over here, whereas the means most of the prior to 3.2 are mostly means between means supercondytic, means between 0 and plus 2, above 0, means in above mature. Whereas as we are going towards the younger, means it is getting towards more evolved and due to the crustal reworking. So that's what I wanted to say here. So that means basically what we wanted to say is that means the signatures of crustal reworking are seen from at least 3.2a, but the first crustal reworking is evident from 3 million years, 3000 million years, and but when it comes to 2.56, both we have the juvenile crustal additions as well as our means some kind of recycling component is also there. So this is what I wanted to say. So with this, I wanted to conclude that the TTG, though we have 3 components we have studied, the TTG derived due to the partial melting of the hydrous basaltic source at means amphibolite to garnetable stability conditions, placed at 3.2 GA, whereas eastern margin, so means it's slightly evolved from means derived from the evolved crustal source at shallow depths, and emplacement 3 and 2.56 GA, whereas the central around 2.56 GA. And we provided this both means age constants for granitic magmatism and corresponding metamorphic events along the Chitraduga greenstone belt. And 2 metamorphic events are well documented with both between zircon and titanite. So, and our study demonstrates that plate tectonics are operative in the central part of the Darwin Keton from 3.2 GA, and the discrete evidence of plate tectonics from 3.3 GA. And of course, morning Sukanta was mentioning means it was much older, means as per the hafnium isotopic history. And but they're whatever it is, but they're more prominent from 3000 million years in Darwin Keton. So final my point is that a combination of zircon geochronology with other geochronometers will help in unravel the magmatic and metamorphic history of a terrain. So with this, I thank the.
So thank you, Dr. Rammohan. Now we can take a couple of questions.
Actually, it's not a question, kind of suggestion.
Yeah, no, yeah, please.
The titanate age is what you have shown. You have plotted it in a vitral diagram.
Yeah.
That's why you are getting all this reverse discordance.
Yeah.
So according to the College Smith 2015 recommendation, so every common blood-bearing other minerals like titanites, apatites, rutiles should be mostly treated with the Tara-Weissenberg diagram.
Okay.
So if you can put it in a Tara-Weissenberg diagram, that reverse discordance problem might change.
Yeah, the reverse discordance, we are finding it, but numbers may not.
Yeah, numbers may not change, but it is not actually reverse discordance. It's actually mimicking. Yeah, because you are using a vitral diagram.
Yeah.
But if you can put in a Tara-Weissenberg. Second thing is that the titanite discrimination based on the uranium-thorium ratios. Very recent recommendations has changed that. Now we couldn't actually distinguish titanates based on uranium and thorium ratios into magmatic and metamorphic.
No, that's what I had given. That is point 2 that I had given.
But that,
3 components I had given.
But actually it is fine, totally fine. But the thorium by uranium ratio based discrimination has been modified. Okay. So now the recent recommendation is that we cannot precisely distinguish between thorium by uranium ratios using magmatic and metamorphic titanates.
Yeah, that I agree with you. The point is that here, that's why we are not relying on one component.
Yes. Still it's correct. Just 2 suggestions. That's it.
I would like to know your opinion regarding the source rock of 2.62 GH Chitradurga granite. Is it a crustal or it's a mantle?
It will be a crustal, sir.
So if it's a crustal, do you think that there is some sort of thermal perturbation that has affected crust at 2.62 GA? So we should get some metamorphic ages in some sediments there?
Actually, Jayananda, I think 2013 paper, Geological Journal.
But that was in Eastern Dharwad Craton, not in the Western Dharwad Craton.
Eastern?
I am talking about the Jayananda paper.
That is in the margin, sir. That is also actually in the margin of the Chitradurga shear zone 2 further east.
Further east, in the Eastern Dharwad Craton it was there.
So he has reported, but we tried, but we didn't get. So we are not sure about it.
Okay.
In fact, we tried seriously for that, but we didn't get, sir.
Also by Jayananda.
Yeah, yes, sir. Yeah, recently he has published.
So that's also 2.62.
Yeah, but this location very recently is published 2 months back.
Yeah.
We wanted to visit that location. Means very recently he has published.
2 months back.
Yes,
but
sir.
that's also 2.62. Our data was 2.62, and this one is also 2.62. It's the same.
So that is actually this new area which he has published is in the so-called. Though means some people say it is the central Dharwad Craton, we call it as the transition zone as per the earlier Chadwick's classification, which is more appealing.
Then it's just following from Shantanu's question. If we are getting a thermal perturbation at say 2.6, and you were suggesting 2, right? 2 thermal events, I think, after.
Yes, sir. We have got 2. Yeah, from that particular study area.
I'm just wondering from the metavolcanics, basaltic metavolcanics. I mean, there the metamorphic history must be recorded in the form of some mineralogical changes, plus also probably some deformation effects. People have worked here, I think, right?
Except actually we have that is a big gap, sir. Earlier, especially in the greenstone belts of Dharwad Craton, very few ages are available.
No, not ages.
Yeah.
I'm saying
means both magmatic
when they
history
say
and
it's
metamorphic history.
No, when they say meta.
So sediments, you mean to say?
No. I'm just saying that if these are metavolcanic rocks or metabasalts, so what minerals do these rocks contain? I mean, if it's meta, it cannot be. It possibly has indications.
They call
right?
it. It's greenstone.
They're chloride, so.
Green schist species.
So I'm saying, so that's what I'm saying, that we should be able to discriminate at least to some extent what things are there. So maybe to correlate would be a good idea.
Yeah.
Okay, I think, thank you very much. So I now give it to my colleague.
We have another presentation. It is also on Dharwad Craton by my young friend Amya Kumar Samal from BHU Varanasi. He will be talking on SCLM evolution.
Good afternoon, everyone. Taking the discussion into the Dharwad Craton, In the next 15 minutes, I am going to discuss about the paleoproterozoic mafic dike swarms of the Dharwar Craton. I will basically focus on our studies that we are conducting on the geochemical characterization of the dikes. This is a very beautiful image that is collected from the Dharwar Craton on the Google Earth platform. As you all know, mafic dike swarms typically constitute hallmark representation of mafic igneous activity associated with rifting or plume events. They are greater vertical depth, worldwide extent, and ability to retain high-quality uranium-led geochronological data in the form of zircon and bedellite, geochronological data, paleomagnetic data, make them an ideal proxy to solve many of the geological problems. When they are associated with a mantle plume, they are considered to be the plumbing architecture of a large igneous province. What they basically do, they transports magma from the deeper reservoir to the surface. This is the diagram what Professor Srivastav discussed in the morning session, but here I want to emphasize the plumbing architecture of the mafic dikes can be classified into 4 levels. In the level 1, basically the job of a igneous petrologist to characterize the mantle source. Here the source can be of asthenospheric mantle. When a mantle plume interacts or comes, when this plume head interacts with the lithospheric mantle in the level 2, the magma composition can be changed due to interaction with the lithosphere, or this lithosphere can be a subcontinent metasomatized lithosphere. Accordingly, the geochemical signature of the mafic dike swarms vary from a asthenospheric signature to the lithospheric signature. Coming to the level 3, when this dike magma comes to the crust, they spreads in the form of dolerite and dikes or sills. Coming to the level 4, the dikes spread on the surface and forms flood basalt sill provinces. Coming to the importance of these mafic dike swarms, they are very helpful to study and understand the evolution of the subcontinental lithospheric mantle. As I was saying, in the Precambrian, these dikes, the flood basalts are generally eroded, giving a superficial exposure of the mafic dike swarms. Therefore, these dike swarms are helpful to understand and identify different Precambrian LIPs. As you understand, the dikes follow the regional stress pattern. Therefore, they are helpful to reconstruct the paleostress regime. As the dike swarms spread not only a single cratons, but also worldwide, therefore, they are helpful to establish the cratonic neighbors during their eruption. As the mafic dikes, magmas are basically mafic and ultramafic in composition, therefore, they are helpful to prospect different mineralogical or economic potential. So, what we do when we conduct a study on mafic dikes? As you understand, for a study on mafic dikes, the trend is important. If we don't know the trend, the dike study has no meaning. When a dike comes to the surface, it always comes with many friends. It never comes alone. So, our job to characterize the friends of a dike means to group the dikes into different swarms. And this precise characterization can be done through the help of uranium-led geochronological study. Some provisional characterization or grouping can also be done by the help of geochemical characterization, but it is not a precise tool. Second job, what we do, after the grouping, we identify the geometry of the dike swarms, taking into spatial and temporal correlation how the dikes are spread in a particular craton or how the dikes spread into the neighboring craton. By following the grouping of the dikes, in last few years, we have prepared the dike map of the Indian cratons for Dharwar, Bastar, Singhbhum, and we are going to publish a book on this map of the dike swarms, which will be published in some years. So, coming to the Dharwar craton, it is a classical terrain to study mafic dike swarms. Why I am saying I have sufficient evidence? Because the dikes in the Dharwar craton, they spread a wide range from 2.37 to 1.79. And the density and concentration as well evidenced from the dike map you can see. And interestingly, they have a multiple trend. Whatever trend you will say in the Dharwar craton, you will get the trend of this dike. And second thing is that it has a wide spectrum of geometry. If I will come to the geometry, if you will say the 2.37G Bangalore swarm, you can see the blue color lines, they have a classical radiating pattern you can see in the this area, in the Bangalore around area, they are mostly east-northeast trending. On the northern part, they are northeast trending. Some people suggest that the plume center on the western side of the Dharwar craton, but some evidence suggests that the dikes plume center can also be on the eastern side. Their proposal is that because the dikes, concentration of the dikes is more in the eastern Dharwar craton, they suggest that there may be plume center close to the eastern Dharwar craton. There is still controversy is going on. Coming to the another classical radiating swarm, that is 2.21 GA, that is purple color. These dike swarms are northwest trending in the Anandpur area, and they are east-west trending in the Hyderabad area, where we suggest that the plume center located somehow in the northwestern part of the Dharwar craton. Another classical radiating geometry, 2.08 GA swarm, which are well distributed around the Kadapa basin. In the northern part, they are northwest trending. This red color you can see, these are well dated. All these subswarms are well dated. These are northwest trending. And here, these are 2.08 swarm. These are northeast trending. So these three swarms suggest a classical book example of the radiating pattern. So what research questions we are going to address? In this study, we'll basically focus how the subcontinental lithosphere mantle of the Dharwar craton has evolved by studying the geochemical characterization of these 9 generations of paleoproterozoic mafic dikes. And we'll understand how the proterozoic mantle has been evolved, what is the cause of this mantle evolution. And we'll precisely estimate what is the source composition or precisely composition of ACLM. And the most important controversy, whether these dikes are part of different mantle plumes or how they deviate from classical plume chemistry. There is sufficient amount of geochronological data available on the precise geochronological data available on these paleoproterozoic dikes. The study starts from Hall et al. 2007 and subsequently French and Himan 2010, and recently Soderlund et al. Has given a spectrum of age for the paleoproterozoic mafic dikes. Similarly, several authors have also studied or characterized the geochemical nature of these paleoproterozoic dike swarms, and we are also conducting this geochemical characterization. Coming to the detailed study, I want to emphasize here, here I have shown 4 generations of paleoproterozoic mafic dikes, 2.37, 2.21, 2.08, and 1.89. If we'll see, all these dike swarms show a classical crustal signature. The prominent niobium tantalum anomaly, TI anomaly, and you can also see all these dike swarms. This classical crustal signature can be, we can interpret in a 4 way. That can be a subduction signature, which is not totally impossible, because the Dharwar craton has been cratonized at 2.5 GA. There is no chance of any subduction event in the paleoproterozoic. And second, there can be a crustal signature when magma comes to the surface, they can interact with the crust. Third, this can be a critical signature of assimilation fractional crystallization, what is taking place in the magma chamber. Or that can be a signature of a metasomatized mantle. We'll gradually understand which signature bears a primary role for the geochemical evolution of these mafic dikes. In the chondrite normalized RE pattern, you can see they show LRE enriched pattern with flat HRE. The LRE enriched pattern is also suggestive of a typical crustal signature. What to basically understand, if you'll compare the RE and multi-element plot, you can see their signature, RE and multi-element signature are more or less similar. What this similarity suggests, this similarity could be due to a similar mantle source composition. If we'll consider these are of similar mantle source composition, this suggests the paleoproterozoic mantle has not evolved much from 2.37 to 1.89. This suggests a similar tectonic setting, 2.37 GA to 1.89. This is not new to the Dharwar craton. If we'll see in the Kannada superior craton, the similar kind of tectonic event has happened from 2.5 to 1.7, where a stable tectonic regime has happened that lead to the crustal rifting by emplacement of different generations of paleoproterozoic mafic dikes. We try to understand the role of assimilation fractional crystallization. In 2019, Ashutosh Pandey and Chalpati Rao sir has carried out a study to understand whether AFC process has played a significant role. You can see, although many elements follow the classical trend of the AFC, but you can see in several plots, the data doesn't follow the trend. We have also conducted for 2.25G and 2.08Ga, and you can see the scatter of the data. That basically suggests AFC has not played a significant role in the genesis of the magma evolution. I will come to the crustal part 1 minute later. Before that, I want to emphasize, we have also studied the 2.08 dikes, the intra-swarm variation. This is subswarm 1, this is subswarm 2, this is subswarm 3. The paper is recently published in the Precambrian Research. One of my PhD student, Srinjay Datta, is working on this. You can see the SS3, which shows a primitive signature observed by the higher Mg number, higher nickel and higher chromium content. On the other side, the SS1 and SS2, they are doesn't showing a primitive signature, rather they are more differentiated or evolved type of composition. So by plotting the variation diagram, we understand they are derived from a common mantle melt evolved by the fractionation of olivine, clinopyroxene and chrome spinel. We have also carried out anisotropy magnetic susceptibility study to understand whether the magma flow in these three subswarms has uniform or not. Interestingly, the subswarm 1 and subswarm 2, they show vertical magma movement, where subswarm 3 shows horizontal magma movement. By plotting anisotropy with the susceptibility, we understand the primary magma flow is controlled by mineralogy rather than the tectonic control. So, if we'll see the gravity map of the Dharwar Craton that is published by NGRI, ONGC and GSI long back in 2006, the SS2 that follow gravity law, that is due to Kurdu-Wadi lineament, and what Saibal sir was asking, I want to emphasize, when a plume interacts with a lithosphere, different kind of stress regime plays. If you are studying an area which is close to the plume center, their plume has a significant role. But if you are moving away from the plume center, there are crustal inhomogeneity in the form of fracture, in the form of shear zone, that I want to emphasize here. This lineament has played an important role in the generation of the magma from subswarm 2. For the subswarm 1, here GS2, that is a gravity high and that is observed, that is interpreted by Rana and Rao, that suggests a crustal thinning and active rifting may be due to the interaction of the mantle plume. Here we suggest the emplacement for these three subswarms. One is stage 1 and stage 2, where stage 1 follow the emplacement of SS3 subswarm 3 diaxons, and SS2 1 and 2 follow the stage 2. The last segment that I want to emphasize here, we have also characterized the trace element composition of the olivine to understand whether the metasomatized mantle has played a significant role or not. A classical paper by Sobolov et al. 2005 and 7 that suggests when a subducted crust interacts with a peridotite mantle, means high SI melt interacts with the mantle peridotite, we produce a olivine pre-pyroxenite with some remain of unreacted peridotite. By taking this model into account, we have compiled some of the dikes that precisely contain olivine, because most of the dikes are evolved in the Dharwar Craton, therefore they seldom preserve olivine grains. We have selectively collected some of the dikes which contain olivine. You can see the olivine grains are here, and we selected different ratios which are not controlled by the fractionation process, and by plotting this data, we can see the composition are not precisely peridotite or not peridotite or pyroxenite in composition. Therefore, what we suggest, by following the model of Jayananda et al. 2013, we follow that the Dharwar SCLM of the Dharwar Craton has been evolved due to the subduction process or accretion between the WDC and ADC. These subduction, multiple subduction fronts are present, which are metasomatized the SCLM, that is below 2.52, and subsequently the plume has interacted with these metasomatized SCLM and produced different generations of dikes. This is the last slide. What I want to emphasize, In the plume signature, in the Dharwar Katon, little bit difference. What difference? There is no plume lies below the Dharwar Katon. Therefore, we don't get any asthenosphere type of signature in the Dharwar mafic dikes. Therefore, peripheral magmatism. Due to interaction with the lithosphere, their composition is significantly changed. We always ask if the plume, where is the asthenosphere signature? Because due to lithospheric interaction, they don't show asthenosphere signature. Universally spread, they are not only spread in Dharwar, they spread in the Bastar Craton, several dikesons in Bastar, Singhbhum, also in the nearby cratons in the Ilgran, and multi-stage emplacement and the emplacement partal radiating circumferential, which can only be established through the mantle plume. So this is my key takeaways. Stable lithosphere during Paleoproterozoic, metasomatic evidence in the Dharwar Katon. Mantle of the Dharwar Katon is heterogeneous due to subduction. The dikes in the Dharwar Katon is basically plume driven, or the mantle source is hybrid, and these dikesons suggest the association with different large igneous provinces. Thank you, sir.
Thank you so much, Dr. Amiya Kumar Samal. Can we skip questions? Well, Amiya is here for next 2 days.
Dr. Samal, you said that mafic dikes, they come always in swarms. But I have seen many dikes, mafic dikes, which are alone. As for example, in Bundelkhand, east-west trend, different age than the northwest, but that is only one or maybe few. Similarly, in Aravalli Craton also, there are only few mafic dikes that can be observed.
If they are part of a LIP and associated with plume, they always come in a group, not a single.
If they are.
Yeah, yeah. Thank you, sir.
Okay, thank you, Amiya. Thank you so much. We'll move from Dharwar Craton to Bastar Craton. We have next presentation by Dr. Satyanarayana Mahapatro from Geological Survey of India.
Hello, hello. Am I audible? Thank you. Good evening, everybody. I am from Geological Survey of India, and the work I am going to present is a work carried out as a part of geological mapping, and actually mapping, we have done second generation geological mapping in this part of the area. Geological Survey of India normally takes second generation mapping in those areas where the areas were not very accessible earlier, or where the areas say differing opinions, I won't say about the controversies, differing opinions are existing in those areas. So we take up second generation mapping, that is on 1:25,000 scale. So here I am going to present a work on the volcanic rocks of Nangaon group in the central part of the Bastar Craton. If I go to the geological map of that area, you can see here, this is basically the central part of Bastar Craton, where you have Chhattisgarh basin in the eastern side and Deccan troughs in the northwestern side. Then Bastar gneisses of different ages, Paleo to Mesoarchean in the western and eastern side. You can see a very linear green color belt that is occupied by volcanic rocks. And these volcanic rocks are bimodal volcanic rocks. We have basalts as well as rhyolites, felsic volcanics and mafic volcanics. And this is basically the another volcano. This part of the belt is lacks, it has subordinate sediments, whereas volcanics dominant. There is another part that is Khoidagar supergroup, Khoidagar group, which is basically sediment and volcanics dominated, more or less equal amount. So this belt, since early, this has been termed as Dongargarh supergroup. Now coming to here, actually since there are previous work, there were some works have been carried out and lots of differing opinions were there. So we took up second generation geological mapping. In the process of mapping, we also did some geochemical analysis and geochronology, and that work is being presented here. To speak on this Dongargarh supergroup, it has been divided into two groups, that is Nandgaon group and Khairagarh group. For the Nandgaon group is two formations, Bijli rhyolites and Pitapani basalts, and Khairagarh group has 6 formations. And this Nandgaon group is intruded by this Dongargarh granite sensu stricto. There are granites of similar ages have been reported in the north, that is Malanjkhand, and in the south also, the Kanker, etc. areas were there. Now this belt, this belt is typically about 250 kilometer long north-south trending belt, which comprises of thick sequence of mafic and felsic volcanics, and is a bit subordinate sedimentary. Now, typically to tell about the rhyolites, how they are occurring, you can see here 3 petrographic variants are there. Largely the rhyolites are pyric, porphyritic, and the phenocryst proportion differs. Some of the variants, they have both feldspar as well as quartz porphyries phenocryst. Some have only quartz phenocryst, and some are no phenocryst. Typically, maybe you can see the photomicrograph, there is a layering is there, and few microphenocrysts are also still there, only the scale varies. So largely to tell that these rhyolites are mostly phenocrystic, and the phenocryst are almost 30–35% in proportion, modal proportion, and both the feldspars are mostly both potassic as well as sodic. Now coming to Pitapani basalts, these are basically mafic volcanics, little bit metamorphosed to weak to green schist facies, and some more largely massive, but some parts there is a fabric is developed, planar fabric, secondary planar fabric is developed. These are mostly very fine to fine grained and aphyric, no phenocryst, only very few phenocrysts are there for clinopyroxene, and some of the parts relict igneous texture is also preserved. You can see here variolitic things, and mostly the basalts are either intergranular or intersertal with a little bit of phenocryst in different segments. Now coming to geochemical characterization of these basalts as well as rhyolites, you can see here typical character. Only point I would like to emphasize is that in case of basalts, the magnesium is varying in a wider range with low total alkalis and moderate range of nickel and chromium. Similarly, rhyolites, they plot sensu stricto in the rhyolite field as well as the basaltic or andesitic basalt field, but rhyolites, they are mostly highly siliceous, moderate in Al2O3, very low magnesium, and their iron content varies. Now coming to just before telling about what is the petrogenesis or how it, what is the source characteristics, etc. As a usual standard is that to test whether it is alteration or elemental mobility is there or not. We can see here they have low LOI content, coherent RE as well as trace element patterns. Zircon generally maintains they have a trend with the LRE, HRE as well as other trace elements. So we presume that these geochemical characters preserve the primary magmatic features. Now see, green color is for the basalts and pink color is for the rhyolites, and at the same we can see here they have low total RE, moderately fractionated RE pattern with absolutely no European anomaly, slightly more fractionated LRE, more or less flat HRE pattern. Whereas in case of basalts, we have a very significant European negative anomaly. And if we see this multi-elemental primitive mental normalized plot, we can also see that these basalts do have enriched LILE over HFSC, negative niobium, tantalum, and TI anomalies, positive lead anomaly. At the same time, you have vessels, which is in addition to that, we have barium strontium anomaly also. So mineral chemistry, as I already told, mostly in case of vessels, we have some clinopyroxenes which show a trend from the diapside to agate, and low TiO2 content, moderate Al2,3 content. Rest, the other thing is that previously, though many have worked, but in this work we have also found presence of chromite in the ground mass of the vessels, and we have done some study. These are mostly aluminous chromites. Then we have dated 2 samples of the rhyolites in IIT Kharagpur, where the dates mostly we have, these are the CL images, we indicate magmatic ages, which comes to about 2.54. One sample is giving 2537 plus or minus 29, another is giving 2543 plus or minus 45, slightly little bit spread. But the other sample also have a Concordia age of 2332, that is preserved. Now comparing with the dates, available dates, we can see that in the area we have actually this studied is the central part of the Kotri-Dongargarh belt, where the volcanics are slightly wider in presence is there, where we could get a slight, see the middle point is, if we take, we have a age which is slightly higher than the, older than the previously. This yellow part is mostly for rhyolites, the blue, green is for basalts, and this pink is for mostly granites. This is Dongargarh, and these are from Melanchkhand. So we can see here there is a pattern is here. Mostly previously they have reported say Paleoproterozoic, but maybe it is late Archean. So now coming to the trends, you can see here they are showing decreasing MGM. So we see a clear cut trend of fractionation in all the things. Initial fractionation was mostly by controlled by olivine and clinopyroxene and chromite. And when we study the rhyolites also, we see that there is a fractionation trend of TiO2 and SR, plagioclase and ilmenite fractionation. But the link between the rhyolites to basals to rhyolite, this is also tried to see how it could be there. And that is, we can see a coherent relationship in all these diagrams. Later on, we tried to see the crustal contamination, whether it is there or not. So different plots that we have attempted, they doesn't show much role of crustal contamination in the evolution of the magma. This is more the basaltic magma mostly. Now, after that, we tried to see the source characteristic.
Sir, you have 2 minutes.
Yes, that's why I'm going quickly. So, source characteristic, when we started to see the source characteristic, we could see that there is a enrichment that is not by the fluid, but by the fluid, this influx of the sediment melts rather than the fluids. So the thing is that whenever we try to study the petrogenesis of rhyolites, we normally think of whether it is a partial melting of crustal rocks or fractional crystallization. Clearly, we see a trend of fractional crystallization, and then we try to see the test with the AFC model, and this AFC model says that where we have initially we have taken a primitive basalt with MgO 10% around, and we try to mix with the Buster gneiss, and we could see that this composition of the rhyolites can be achieved with 30 to 40% AFC with the of Pitapani volcanics with Buster gneiss, and but the rate of rate is 0.5, which is normally not very acceptable, or say. Then we have tried to do with the slightly evolved MgO basalt with MgO 6% around, and we could see that the most of the composition of the rhyolite can be achieved by 20 to 30% of assimilation of the NCESS, that is at a rate of 0.26, that is more or less a year. So there is a possibility that what we try to see is that tectonic setting says that there are so many things have been told, continental rift, mantle plume, island arc, back arc, but we don't see such things here. Our chemistry of the basalt show that they are mostly generated during the subduction related process, and this is also evident from the different discrimination plots that we can see that they show the similarity of the continental arc signature similar to Andes and Cascade arcs. So you can see all three diagrams are showing the same characters, and this is also supported by their multi-eliminal test plots. This is contrasting with OIB and more, whereas it is similar with the continental arc. The same thing is also implied from the mineral chemistry of the clinopyroxene as well as chromite. So here we think that there is a idea that Buster Craton has two terrain model has been recently proposed, where they say that there is a middle the central Buster erosion that volcanics, and we think that we also propose in the same alignment that probably this magmatism occurred in the central part of the Western Craton is analogous with the Andean style of continental arc magmatism. So this is the inferences. Thank you very much. I took little more time.
You can read that. Any questions? Yes.
Dr. Mahapatra, 15 years back when we were doing fieldwork with BSc students, myself, Rajesh, we stumbled on a boninatic dike which includes the Bijli rhyolites. And we came up with a paper that there was a fossil subduction zone 15 years ago, published in German journal.
Maybe on the western side of that.
No, in the Bijli.
Rajnandgaon.
While Rajnandgaon side, while going from Nagpur to Raipur, once you cross that Dongargarh temple, na? So we have, that actually corroborates, the major outcome of your work, actually.
Thank you very much.
Dr. Sarkar.
No, sorry.
Okay.
Please.
Sorry. What I understood is that you have shown the total RE content of your basalts is much more than that of the rhyolites.
No.
Or
no.
I understood it wrong.
No. Basalts is less than rhyolite.
Okay, then it's the opposite. Okay.
Maybe.
Thank you, Dr. Mahapatra. Thank you so much. Now we'll move from Bastar to Deccan. Next talk is by a young geoscientist, Dr. Anmol Naik from Goa University.
This is the pointer. Yeah, got it. Hi, good evening, everyone. Today, let's embark on a fascinating journey into the realm of physical volcanology, where we'll look at some intriguing rhyolitic rocks from Saurashtra. The monotonous nature of the Deccan Traps, where we have a thick pile of flat-lying flood basaltic lava stacked on top of each other, whose 65 million years worth of erosion has given rise to this beautiful step-like topography and flat-top table mountains, is seen to depart in Saurashtra, where the volcanic units have acquired tectonic dips, and we get rocks of considerable compositional, textural, and structural diversity. The current study focuses on the area in the south eastern part of Saurashtra, around the towns of Rajula, Savarkundla, Garyadhar, and Talaja, covering roughly 7,000 square kilometers, where the area is mostly flat and low-lying, occupied by basaltic lavas, which are overlain by recent alluvium deposits. The southwestern portion of the study area, however, has been traversed by numerous rocky ridges in the form of seawards dipping cuestas. Now, these cuestas are made up of basaltic lavas, and basaltic lavas that are overlain by silicic volcanic units, which is the focus of this particular study.
Please note how some of the field photographs over here, note how most of the hills over here have pointy tops instead of flat top hills in the central portion of the Deccan Traps, or the majority of the portion of the Deccan Traps. This is because of block faulting that was associated during their formation, which was attributed to the southeastern Saurashtra flexure, which has given rise to the dips to these volcanic units. And the gentle slope over here defines the dip of those volcanic units, whereas the steeper part that were the then fault-bounded escarpments, which are now exposed due to erosion. The silicic volcanic units are tens of meters thick, and they extend to roughly 20 to 30 kilometers in length, and they are characteristically flow-banded. Now, these flow bands over here are deformed, or they preserve folds of rheomorphic deformation. Practically, we get all the features that one would expect in a ductile shear zone, from intrafolial folds to isoclinal folds to sheet geometry, recumbent folds, and all these F1 generation folds are again refolded into folds of F2 geometry. Now, the big question over here is whether these units, these silicic units, are products of effusive eruption forming lava flows, or whether these are high-grade ignimbrites. Because high-grade ignimbrites and effusive lavas, they mimic structurally as well as texturally. Now this is very important when we consider the environmental impact of volcanism, for a simple reason that explosive silicic eruption or explosive eruption can inject ash and magmatic gases to a much greater height into the atmosphere, causing significant distribution or significant wider distribution of those volcanism as compared to its effusive counterpart. How do we distinguish it? We need to carry out strategic investigation with regards to field and textural characteristic. The first thing which we do is we investigate the contacts between the underlying lithologies. We look out for basal breccias, because when lava flows get emplaced, the top part of those lavas cool quicker, they contract, and they brittly fractured into smaller clinkers, which are then overridden in the way they're getting emplaced. The second part is to look at textures. We check whether there are vitroclasts which are present, indicating explosive fragmentation of those magmas. And then we can also look at vitrophyres if there are any present. The first thing which we found was presence of basal breccias. These occupy depressional surfaces, and they basically represent zones which are, I would say, these are the zones which have fallen in front of the flow front and then have been overridden. The flow top breccias are now becoming flow bottom breccias, giving us a small indication that these are probably indicative of effusive eruption. We studied their textures as well, and over here we can see that these are crystalline textures. It's a very fine-grained rock, characteristically porphyritic, but please note that the phenocrysts over here are representing more of mafic assemblies. Over here we have pyroxene. I'm so sorry about the poor quality of the image, but these are plagioclase phenocrysts. By the looks of it, a little bit more on the calcic side, so it's quite rare to see calcic plagioclase and pyroxenes in rhyolitic rock types. The ground mass is characteristically fine-grained and exhibits something which is called as a snowflake texture, which is very similar to a poikilotic texture where we have aligned macrolites, which are enveloped completely by either quartz, anhedral quartz, or K-feldspars. We also get vitrophyres at the base. Now, vitrophyres can be tricky because they can represent both. They could represent either very high grade or the highest grade that one exhibits during explosive eruption, highest grade of melting that one can attribute during explosive eruption, or they could be just the chill basis of lava. We had to check what the textures were. One is pitchstone and the other one is vitrophyre, and by the looks of the texture, the continuity with the core and continuity with what we see within the vitrophyre, we can see that these are glassy ground mass, which are again set in a extremely crystal-rich matrix. Again, please note that these are almost mafic glomerocrysts of calcic plagioclase and interestingly orthopyroxene. I don't know why. Less commonly clinopyroxene and olivine over here, indicating that these are chilled bases of lava flows. So what we have over here are not high-grade ignimbrites, but a large-scale rhyolitic lava, which we can classify it as flood rhyolitic lava. This is one of the photomicrographs which I love. These are very high resolution images, or like extremely zoomed in image of the pitchstone that we found. We can see acicular fern-like feathery growth of feldspars. You can see those microlights getting attached over there. It's like a snapshot. Somebody just paused the crystallization process over here. Now the area also records an impressive history of explosive silicic eruption in the form of low to medium grade crystal-rich ignimbrites, which can be seen over here, where we can see eutextic texture that is where we can see eutextic texture that is very nicely preserved. This is a photomicrograph which shows that eutextic texture. Here we have pumice fragment, which is a vitroclast, showing stretched vesicles, which is set in a relatively undeformed matrix of broken crystals and broken vitroclast, indicating that the pumice, when it was within the vent, was experiencing deformation due to volatile expansion and not deformed during or like after the deposition that took place. This is a more higher grade of welding, a medium grade welding, which is characteristically preserved. It preserves the eutextic texture, which is defined by more flattened pumice vitroclast, and again, crystal-rich and fine tufaceous matrix. Again, pyroclastic activity. Now, we have this extraordinary development of lithophysae, or thunder eggs, which they are called as. These are spherical, ball-like structures with concentric growth and irregular cavities that are often filled by secondary minerals such as quartz. This indicates that the pyroclastic deposit with which they are associated were extremely gas-rich, and they were not a product of fallout deposit, but these were products of pyroclastic density currents, extremely gas-rich, again, very crucial with regards to environmental impact of these volcanic activities. So they were so dense that, locally they were present in like hundreds and hundreds of thunder eggs, present as both, like we get single units, we get twins of it, we get triplets, we get quadruplets, and so on. We also get, in the northern part of the study area over here, there are these massive tuff breccia ridges. These extend to more than 20-25 kilometers in length with their minimum preserved thickness, and these are walls of rock which come up, or they rise like 70 to 80 meters above the surrounding plains. These have subvertical contacts with the surrounding basalts, indicating that these are some sort of fissures that are again present over here in the form of an echelon geometry, indicating that these were probably some of these, what I would say is like fissures for the pyroclastic volcanic activity that is preserved within this particular study area. This is what they look like. We are standing on one of the fissure. They are aligned. You can see that some of the overlap is present over there as well. We also see one of the prominent ridges of the lava flow, the crystal-rich lava flows that are present. I think this is Burman Mota Ridge, and this is one of the tuff breccia ridge that we saw. These are amongst the lower lying ones. The massive ones were a little too difficult for us to photograph and didn't really have a good picture of them, so not included over here. They are ferruginized and they are silicified, probably because of secondary hydrothermal alteration, or like I would say, hydrothermal activity at that point of time. Alteration would probably be a wrong term to use over here. This is a wrong picture. I wanted to add one more picture over here. This area also preserves a large-scale magma mingling features where we have basaltic magmas that are interacting with these silicic rocks all throughout. So these silicic magma chambers had some sort of interaction with basaltic magmas as they were getting formed, which was indicative from the textures, as well as in field. I'm so sorry about the field photographs. I don't know how it happened. Indicating that basalt or basaltic magmatism, the mafic magmatism in that area, probably had some material as well as thermal input in the petrogenesis of rhyolites from this area. So to conclude, this particular region has widespread and extensive silicic magmatism that is preserved over here of both varieties, the crystal-rich effusive lavas and crystal-rich pyroclastic rocks of medium and low-grade regions. The area also preserves some sort of tectonic disturbances that has occurred in that particular region in the form of block-faulted flexures, the southeastern Saurashtra flexure which we have seen. Thank you so much.
Great.
Yes, sir. Anmol, very beautiful pictures you have presented. I am just curious, you showed olivine with rhyolite.
Yes, sir.
Is that olivine what? What's the composition?
The thing is, we have not yet carried out the EPM analysis on them, and there are very rare olivines, like most of them are orthopyroxenes which are present.
Yeah, but you know, phosphate cannot coexist with the free silica.
Correct, sir. I think like
it could be phthalate.
Yeah.
It has to be phthalate.
It probably would be a little bit, it would be more towards Fe range, like Fe part of it, but not exactly phyllatic composition. We have phyllatic olivines within Deccan basalts or within glasses that are associated with Deccan basalts.
Phthalate is fine, but phosphate is the problem.
Phosphorite, I don't think so, sir. Very, very rare.
Phosphate and free silica, they cannot coexist actually.
I don't think, they are phosphorite. So I think they would be like FO50 in that particular range. Like if I had to guess. Yes, sir.
I have one question. Yes, that is, during your presentation, you are talking that mafic magmas and they mixed up or contaminated with silicic rock.
Correct.
So what was their effect? I mean, in the petrological point of view, I mean, the extreme heat of basaltic magma, could they melt the rhyolite fragment? Is it very common in that case? So you made a passing remark that it had affected the petrogenesis of basalt. So I want to know some more detail onto that matter.
So there's one paper which we recently published, I think so it was last year or something, which was on one of the dikes from this particular study area, and we had isotopic evidences suggesting that there was some sort of material input from the basalts and some sort of material from the continental crust itself. So rhyolitic melts are mixtures of both. We had basaltic magmas, we had, yes sir, there is some sort of assimilation that was taking place. Texturally, it shows that there were mafic chambers because of high crystal content within those rhyolites. And those crystals were unlike the previous talk which we saw, where we had phenocryst of quartz and K-feldspars. Over here, they were more of mafic assemblage. Yeah, more gabbroic cloths, I would say, at that point of time. Yeah, so the thermal input would be very prominent, where due to repeated diking activity, it would heat up the continental crust. That melts and we get rhyolites. And then again, like second part, I would also say that they also played a crucial role in triggering the eruption, because it enters the chamber at that point of time, causes some sort of distabilities at that point of time, triggering eruption.
Yeah.
Yes.
Anmol, good talk. I wanted to know that those fissures that you are saying, so are they pre-existing fissures through which the magma is injected, or are they actually magma-induced fissuring?
I think they are magma-induced features which are there. I don't have the presentation over here. I'll show it to you. But these are the ones, these are dikes. I mean, to be plain and simple, these were massive dikes which were there, 70 to, I mean, they were at least like 30, 40 meters thick to be on the minimum part of it. And like massive, 25 kilometers was the minimum length which I think. But like if you look at it structurally on Google Earth, they would go like more than that. Yeah. No, these are dikes, proper dikes. Yeah, proper dikes of pyroclastic material which were there instead of, coherent magma. Instead of coherent magma, we had pyroclastic material.
Any more questions? Okay, thank you, Anmol. Thank you so much for completing within a given time. So with this presentation, we end our session number 4. I thank Professor Mandal sir for co-chairing this session, and I also thank Rao sir for giving this opportunity to us. Thank you so much. Over to Sneha.
So again, now I will request Director sir to give the memento to Professor Mia Mondal and Professor Ashish Dongre. And now I will request Professor J.S. Roy and Professor Shukanto De to chair the next session.
Thank you, Sneha. So many thanks for giving us the opportunity for chairing this session. So in this session, session 5, there would be 4 presentation, and I could see the details, and I have come to the conclusion this is LIP related session. So the first lecture will be by Professor Sarojit Sen Sharma. So now I would hand over the mic to Professor Sen Sharma, my younger brother, to give his nice lecture on long-lived large igneous.
Put it here. Okay? Which one? Here. Good afternoon, everyone. I am told that this conference is primarily targeted, made for by them, the students and the young research scholars. My presentation is intended basically to them. Students, my students actually participated in preparation, but they could not make it because of different reasons. Actually, as we are learning more about LIPs in last 20 years, LIP's definition itself is probably changing. It is getting revised time and again. Initially, Coffin and his worker team, more than 20 years ago, what they identified, LIP is basically for mafic provinces, large areas, millions of square kilometer areas to be formed within, say, 1 to 10 million years. This is just the major concept. And it has to be within plate space. Now, with the significant development has been taking place since 2000 onward, that even mafic LIPs do have very good concentration, good amount of silicic rocks. And I must say that our friend Hetu and his group has contributed immensely from Deccan in understanding this idea. Now, slowly we developed the SLIP, silicic LIPs, and at that time it was a notion, ideas that 2 rocks cannot stay together in a significant way and sub-equal proportions in a given province. But bimodal LIPs were identified, and now increasingly more and more LIPs, mafic LIPs, they do have a very significant quantity of proportions of silicic components. And of course, the earlier it was very confined that it has to be 1 lakh square kilometer area. Hetu contributed that it could be 50,000 square kilometers, then more than that. It has helped actually to recognize the Precambrian LIPs that I'm coming to this point. The very significant part of time duration that we're talking about. Couple of years ago, we compiled some data from the very known LIPs across the world. And we got, of course, within 10 million years, most of the provinces are there. But also, there are some provinces which are showing peak more than 10. It is going to 30, 40 like that. And silicic provinces were identified that it could be 30, 40 million years. And longer time span even are coming from LIPs. These days, Kerguelen LIP has been identified to be more than 30 million years, geology paper, and some other high Arctic provinces, etc., etc. But present concept is that massive transient basaltic volcanism takes place in a smaller period of time, but pulsatic magmatism is possible in LIPs, and that may be of extended time duration. Now, we are compiling this global data set, and true that now we are thinking that the LIPs could be maximum of about 50 million years. But irrespective of the composition of the LIPs, if we plot globally, then we see that, yes, it is most of the cases maybe probably within 50 million years, but there are also some cases which are extending beyond it. And even some mafic LIPs are also there in this plot. When we are taking further, we see that some of the LIPs, which are 30, 40, even 50 million years or more than that, they have a significant proportion of silicic rocks. And of course, there are one or two exceptions for there, like Tarim and the other one. But there are some significant proportions of silicic rocks are there. But now the duration, extended duration beyond 50 million years or about, is it linked to the silicic composition? This is a question. Now, when this time scale over which these systems are coming up, we are now getting interested more and more that what is happening below. Because the characteristics finding is that adjacent areas of the LIPs, volcanic areas, there are some important plutonic rocks which are dated to be coeval in nature, and sometimes they have been found to be co-magmatic. Now, question has come that whether these plutonic rocks are linked to these eruptions. Now, these questions are haunting the LIP community, and it is being increasingly recognized that LIP system probably vertically extended. And geological, geochronological, and petrological studies are now in focus that how to decipher this link. I was trying to find out that if these three questions can be addressed, that if and how the LIP rhyolite and granites are linked, I am particularly concentrating on the silica-rich part, and how in this case mantle is involved. And if longer duration of silicic or bimodal volcanism is taking place, how they are linked to this volcanic and plutonic processes. Global, if we plot on the delta O18 versus strontium isotope data across the globe, there is a remarkable trend is there, where some of the plots are even coming towards the mantle. Yellowstone is not plotted there. Yellowstone data should be included. That is there, and some of the cases, even the values are below the mantle values for the rhyolites. Now, these low delta O18 rhyolites is an issue there, and here we interpret, it has been interpreted that this spread has taken place because of the different relative contributions of crust and mantles into the genesis of these provinces. Now, this association of altered rhyolite and these your granites, low delta O18 values, ascribed to the hydrated crust. Now the question is that hydrated crust, how did it go there? These questions is probably SLIP would help to understand. Now, point is that to identify these volcanic mafic provinces, a plutonic and volcanic relationship, very, very rare, because this lava is flooded, so the underlying part is not visible. But here, Precambrian LIPs could be of help, because they are tectonically tilted, and there is case that your volcanic rocks is still present, and the underlying rock could be exposed. And so some plutonic rocks could be, some Precambrian provinces are important. So before going that, these volcanic plutonic connections could be established or not established by three competing hypotheses. One is that volcanic and plutonic rocks are basically, you are basically bringing one bucket of mug of water from a bucket of water of one bucket of water. So compositional changes will not be there, but one is giving rise to the plutonic rocks could be linked by giving rise to the eruption. Another idea is that if you have taken up, sucked some material out of it, then the remaining part, residual part, has to be showing you the complementary geochemical relationship. Now, another possibility is that nothing is there. There is no link. There are two separate systems, probably another plutonic process could be linked, which we don't know. There is no as such relationship. I was testing these three alternatives in two cases. First case is Malani. Malani has well-known province. It's a very well-known recognized SLIP. You can see that basaltic magma has intruded into it. The granitic body right-hand side is an associated granite in the field. I did not have that figure right now. And there are also mafic clots within the rhyolites, which have been interpreted to be that interaction of the two melts. Caldera structures is very visible there. They have shown the ring structure and all these things. And presence of high-level plutons are exposed. Zircon delta weight in value low. These are all characteristics of caldera structure. Now, caldera structures has a interesting part, but because it can take you the volcanic rocks down, and that is why you may have a chance to get hydrated material below. Now, with this mineralogy and date, we are getting more or less overlapping close by date. When you plot the geochemistry, major element and trace element, they show overlapping characteristics, and there is a reason to believe that probably they are related by petrogenesis. There are RE plots very, very close by, and they all look similar, and these are the dates, published dates. I have taken most of the dates from your Singh's recent paper in 2023. But important point, that granite is getting plotted not as granite, it is Monjo granite. This is important because I will come to this point. It is intermediate chemistry. It is intermediate composition. When this is the all published data from Malani, and here you see that this is your, if you take the similar RE values and pattern, this one. Coming? Yeah. Yeah. This similar pattern, yeah, there probably some rhyolitic melt was extracted, and the remaining melt was there, that was the granite. But the problem is here that this second possibility is that you have sucked some material and the complementary residue is there. Complementary residue matches because if it is it is a granitic source, that it has been monzonitic. That means comparatively more mafic because the more silicic melts have been taken out. But the problem here is that in that case we should have got a complementary RE pattern, which is not there. Both are showing negative europium anomaly. And this is your okay. Now, if I come to the next province, Dongargarh, that your rheoignimbrites, granite and ignimbrites are in contact. It's a very rare locations, and it is showing a very grading relationship. And these are the interactive processes with the mafic melts. It is now biotitized chloride type of composition, but these are the features which indicate that probably the basic melt was interacting the rock. This is a crystal-rich rhyolites. And in the right side, that within the basaltic enclave in the rhyolite, you have pyroclastic quartz. So A is within B and B is within A. So that is why there is a contemporaneous relationship. And it is a melting rejuvenation was going on. This is the chemical signature that if you consider a basaltic comatite type of melt, that about 15% or 10% rhyolitic melt from their visually rhyolite bulk composition can give rise to a silica-rich basalt in that province that is there. Sample is there. The granite and rhyolite have a common major element and trace element characteristics overlapping. And if you plot it in the phase diagrams, that there is a continuous, some sort of a transcrustal relationship could be established, but granite and rhyolite. But if I come to the RE pattern, very peculiar situation. The first hypothesis matches in some cases. Some cases, your complementary relationship is there in some RE plots. So I don't know whether both are working together, how one is earlier, another is later. Maybe different pulses of processes are there. and the intermediate composition is in between there. So it may be a possibility that this is working in some other complicated way which we still don't know, or maybe have to work out further. Jury is out. I'll tell this, that I urge the young researcher to take it up further. Thank you very much. In Ladakh. Not dark. Sir, आपको मैं सुन रहा हूँ. I can listen. Special association. That's right. So I think there are good possibilities that they are kind of. These are the rare sections where these two rocks, one plutonic rocks and the volcanic rocks, have come. You can see that they are close by. In most of the cases, the volcanic should have been eroded out. But in this case, compared to these are very young. Yeah. And that is very interesting. In Phanerozoic provinces, chances are less.
Before when we discussed this, but I think the same situation can be seen on the moon. You can actually get silicic constructs on the moon.
High silicic rhyolites in moon, lunar high silicic rhyolites are being interpreted in
rocks. We don't know if the rhyolites particularly. There are more return samples that.
Okay, high silica rocks. Yeah.
So high silica rocks, which are volcanics, they are pyroclastic. There is evidence from that, and what people think you're getting distinct mineralogical signature.
Yeah.
So that is actually telling you that there are.
And high silica rhyolite petrogenesis is getting very important for lunar studies on our planetary processes.
Problem is that on the moon, I mean, the spectroscopic evidence of identifying silica-rich bonds, that is not very good. So it relies on emissivity sector. There is no other way. That's why we don't know exactly what they're being identified with reasonable confidence.
I tell you, because I plotted these lunar samples, 2012 science paper, and my Bijli rhyolite data, they are all overlapping composition practically. In somewhere in my computer, the plot is there.
We have got a hit upon a very fundamental.
Yeah.
Okay, thank you.
Sir, one question. You have talked about silicic relation, rhyolite and granite. What about basalt and gabbro in Deccan? Is there any association?
Hetu, could you help me? Yeah, I tell you, what a little bit. In Canada, in Proterozoic, there is a mafic province. They have identified the ultramafic rocks or gabbroic rocks, noditate rocks, with their volcanics, and they have correlated. And now they have dated it, and span is 57 million years. And not geochronologically, geochemically and petrologically, they have established that there could be a link.
Why I am asking is, my student Seth is in touch with you. He is working on Singaroli rocks. They are all plutonic. Their age is Deccan, and we don't find any basalt there.
Yeah,
that's the issue.
Probably it may. We have to see further more, and that's why I again urge the youngsters to come up with the young. No, there could be 10 hypotheses, but easy to understand concept. These 3 hypotheses are roaming around, because one, how you can extract one liquid from the other, and what will be the geochemical consequences. we require better geochronological data, more petrological refinement of the models, and probably we need to look into this. It is not over. I am telling jury is out.
So thank you, Parajit, once again. Yes, very good question. So thank you, Sarojit. So for the nice, thought-provoking lectures. So working on that. So now I would request Dr. Ashish Dongre of Savitribai Phule University to give his lecture on Deccan Large Igneous Province, a review of alkaline magmatism and mineralization potential. Yes.
Okay.
Thank you, sir. This work is the outcome of one DST project sanctioned to us. So I acknowledge funding received from the Department of Science and Technology for this work. Although the topic is related to alkaline magmatism of Deccan Large Igneous Province, I won't be talking on all the alkaline rocks. I will restrict myself only to the lamprophyres which are present in the Deccan. Good evening, everyone. Myself, Ashish Dongre. I'm from Savitribai Phule Pune University. My collaborators in this work are Professor S.J. Sangode from the same university, my students, Anshika Singh and Amajit Bhagat. If you see the Deccan alkaline suite, we have vast varieties of alkaline rocks, but prominent among those are lamprophyres, which are small volume mantle-derived magmatism. Then we have cyanides and nepheline cyanides also, which are mostly associated with the carbonatites. Yeah. Then we have kimberlites present in a central Indian Bastar craton. This is about the occurrence and distribution. If you see this map on the right hand side, this indicates the Deccan province as well as different alkaline provinces present in the Deccan, like we have a West Coast Alkaline Complex south of Mumbai, then Chota Udaipur complex is there, Bundwada, Rajasthan, Sarnudandali, Rajasthan, then we have Girnar in Saurashtra, Nirvanda or Kaladungar area, which is present in the Kutch. These all complexes are near to rift settings. This diagram on the left hand side, this is a tomographic image, slice at 150 kilometer depth. If you see here, we plotted the distribution of kimberlites and lamprophyres in a peninsular India, and they show a very interesting pattern of their distribution. I'll be talking on the lamprophyres which are present in the zone 4. Actually, this diagram is from one of the poster presentation, which will be presented by my student Amarjit. So you can get more details on this diagram during the poster session. These are lamprophyre types. We have mostly 3 types of lamprophyres: alkaline lamprophyres, calc-alkaline lamprophyres, as well as ultramafic lamprophyres. Alkaline and ultramafic, they are related to the rift settings, while calc-alkaline mostly in a convergence setting. These are the subtypes of lamprophyres with their main mineralogy present. So we worked on almost all the lamprophyres present in these provinces. They show very varied mineralogy, and based on their mineralogy and mineralogical composition, we can classify these small volume magmas. We call it as a mineral genetic classification of small volume mantle derived magmas. Like for example, we have given here the clinopyroxene classification. If you see the clinopyroxene, based on its composition, you can classify the calc-alkaline, ultramafic and alkaline lamprophyres, as well as you can comment on their tectonic settings. We plotted here mostly all the Deccan lamprophyres, and you can see they show mostly alkaline characters, with some of them trending towards the ultramafic. So based on mineralogy, we can say that we have 2 types of lamprophyres present in a Deccan. One is alkaline, another is ultramafic. Alkaline present in all the alkaline complexes. They are mostly rich in clinopyroxene, amphiboles, mica, mostly biotite, sometimes phlogopite, plus or minus olivine. We have ultramafic, which is actually present in the West Coast alkaline complex as well as Chota Udaipur, reported in a paper of Pandey et al. 2019. It mostly contains olivine, phlogopites, and sometimes clinopyroxenes. Talking something about geochemistry, these all rocks are LRE enriched and HRE depleted. If you see this particular diagram where we plotted here the LRE by MRE and MRE by HRE, we can see here two types of sources for the lamprophires. One is for alkaline lamprophires, and another we plotted here the ultramafic lamprophires. We have higher ratios in the ultramafic lamprophires that indicates your increasing garnet in the mantle source. So we have a garnet larzolytic source region for UML, ultramafic lamprophires, and spinel larzolytic source regions for other alkaline lamprophires. One thing is very clear that LRE enrichment and other trace element pattern in these lamprophires that they indicates actually their derivation from the enriched mantle sources potentially influenced by the metasomatism. Then the question comes, when this metasomatism happened, what was the time of metasomatism? What was the relationship with the Deccan magmatism? We try to comment on this with the help of these xenoliths. These xenoliths we recovered from one Sarnu-Dandali alkaline complex from lamprophire. We can see here the metasomatic fluid present in the xenoliths. We have a carbonate metasomatic fluid here, which occurring as a grain boundary infiltration along the boundaries. Then we have a silicate melt metasomatism, which occurs in the cracks, mostly crystallizing phlogopites. These phlogopites also occur in a host kimberlite, host lamprophire as a xenocryst. We dated those xenocrysts in one of our paper in 2021, and the age of the xenocryst is 68.1 million annum. So we can say with fair degree of confidence that evidence, and this evidence for the younger metasomatism of lithospheric mantle, which occurred during a rifting event, and the separation of Greater Seychelles from India at 68.5. This graph, here we have a rate of convergence between India and Eurasia, those given in the blue line, computed rate of convergence in the black line. We have green line here, or this strip, green strip, it indicates the eruption of bulk of tholeite magmatism during the Deccan times. And the pink line, it indicates the eruption of lamprophires in a Deccan. We only taken into account the high precision ages given in these references. So it indicates the lamprophire erupted actually after the main Deccan basalt event. This is the timing of rifting present after Deccan, the Seychelles rifting, and these all lamprophires are related to these rifts. We also plotted here the kimberlite magmatism. So when you are spreading rates, they gone down actually. So we have somewhere here kimberlite magmatism in the Bastar craton. So these peaks are related with some magmatic activity as well as to some geodynamic events. We worked a lot on this Kala Dungar or Nirvand alkaline complex of the Kutch area. We have a lamprophires here. These lamprophires included in olivine basalts and cyanides. These are the lamprophires having euhedral phenocryst of amphiboles, showing their panidiomorphic texture. Already Dr. Sharma has presented detailed mineralogy of these lamprophires from the Kala Dungar. I will not go into that. We did some paleomagnetic studies on this. These are our paleomagnetic results from 6 dikes, and they show a normal polarity. They also show very low inclination values, and the paleolatitude plotted somewhere around 5 degrees north of equator. While we have a Deccan paleolatitude, it is around 20 to 25 degrees south of equator. So this difference in these 2 paleolatitude indicates that this is a very different magmatism than the Deccan, and it's a younger magmatism than the Deccan. When we plotted it on the apparent polar wonder path, it's coming somewhere around 55 million annum. So these lamprophires are actually younger. So
you can see there is a sudden rise, or there is a rise in the rate of conversion somewhere around 50 to 55 million annum. So they may be associated with this event particularly, because we have like a very poorly explained event here at 50-55 million annum. So our study gets support from this work. There was a Eocene lamprophyre of 55 million annum age reported from the West Coast alkaline Chota Udaipur complex long back in 2012 in one of the Indian International Kimberlite Conference. So yes, we have three types of lamprophyres present in a Deccan. One is alkaline lamprophyre of 65 million annum age. They present in all the complexes of the Deccan. They may or may not associated with the carbonatites. Others are ultramafic lamprophyres of 65 million annum age. They are associated with the carbonatites like in a West Coast alkaline complex as well as in a Chota Udaipur. Then we have alkaline lamprophyres of 55 million annum age. They are mostly present in the Chota Udaipur as well as in the Kala Dungar Kutch region. And this indicates actually, this magmatism indicates that the thicker lithosphere preserved in some parts of the Deccan province and not fully destroyed after the reunion plume event. Just two slides on the mineralization potential of the Deccan. I categorize mineralization in a Deccan into two. Like one is a secondary, which contains bauxite and zeolites. Another is a primary mineralization of RE oxide as well as magmatic sulfides. We have RE mineralization already reported from the carbonatites in the Sarnu-Dandali and Ambadongar areas. In Ambadongar, it went up to auction state as well as in Sarnu-Dandali, still exploration is going on. Deccan actually, it is considered of barren of sulfide mineralization. So particularly nickel, copper and platinum group elements, and such significant sulfide deposits have yet to be discovered. But we have a chances because the majority of economically important magmatic nickel, copper, PG mineralization is associated with the large igneous provinces. We have a classic example of Norilsk in Russia. So these deposits have actually preferential location in a large igneous province. So we need to find such small potential spots actually within a huge large igneous province event. And for that we need strategies for the exploration. I'm talking about here again the Kutch and the Nirvana and Kaladungar area. We have here olivine gabbros and the lamprophyre dikes, including the olivine gabbros, and we found such significant mineralization here in olivine gabbros as well as in lamprophyres. These are some BSE images. We only conducted some preliminary mineralogical studies on this. So these are the sulfides which are rich in nickel, cobalt, copper, and few of them are also showing enrichment of 0.5 to 0.7% of PGs. And these minerals mostly chalcopyrite, pyrite, pentlandite, and cobaltiferous pyrite. You can see the size of the minerals present. They are more than 500 microns. This final. So my thing is, what I wanted to conclude here, we have a prerequisite for such mineralization, which include the sulfide saturation of the magma, and sulfide saturation can be increased by the assimilation of sulfur-rich crustal rocks, and we also need the structural discontinuities for their emplacement. And these two criteria exactly meet with the Nirvan and the this Kaladungar area, where we have intrusions in a Mesozoic sedimentaries, as well as this area is known for their structural discontinuities. So the takeaway message is that Deccan is not barren of sulfide, but we need to find such potential spots for the mineralization in the Deccan area. Thank you so much.
Yes, please. Ashish, very nice talk. Just two things. First thing is, Gautam Sen et al. 2016 dated one of these lamprophyres. They reported 67 million years. Are you aware of it?
I know, sir.
Okay. Second thing is, DK Paul, they did some paleomag work and published in Lithos, which they claim the oldest magmatic rocks based on paleomagnetism. Now, how your things fit into this?
The first Gautam Sen's paper, he only published one abstract telling this 67 million annum age. and that too on only one lamprofire dike. So we did paleomag dating for 7 lamprofires present in the area. So there may be presence of 67 million annum because there are many lamprofires in the Kaladungar. That's the first thing. Then DK Paul et al., they also reported Deccan age for the intrusions, that cyanides and the olivine gabbros. So they reported the older age as well as the Deccan age. So still they are Deccan. Because these lamprofires intruding olivine gabbros, so they must be younger than the gabbros. Phosphorus as a
direct elements. Have you seen?
Phosphorus enrichment as such we have not seen.
You have not seen. Oh yeah, okay. Okay, appetite.
Appetite is there.
Yeah, that's exactly what I am asking.
Okay.
Yeah.
I thought you were talking about the whole rock phosphorus.
I have a small body.
Yes,
Since you have come across sulfide mineral, it's quite, in fact, I went through the thesis of Professor Rao's students. He also reported that they were doing the work. Okay, I think you should look into those sulfides very carefully. And when I come next time to Bombay, I'll make it to Pune. If you have the samples, I will like to.
Sure. Sure. This is just in a preliminary stage. So our paper is under review on these findings.
Question from
Sir, one half of the comment has been told by Professor Rao. One thing is that there is a paper by Kerr where 69 million year lamprofire have been also reported from the Tathian area.
Yeah.
But that the graph you have shown, you haven't shown that paper.
Well, you have to restrict yourself. How like you have reunion plume and to what extent actually you want to extend the reunion plume magmatism. Not temporarily, but spatially also. Because you have a reunion plume influence area that's mostly in the western India. You're going up north and to the Pakistan, there it is reported in lower Himalayas. So it may be related to any other event. But just not related to the Deccan.
Deccan OIB signature, they have reported like that.
Yeah, every lamprofire will get there in a Deccan OIB signatures because they are coming from enriched mantle.
Okay, sir. And that 55 million year age actually, that is on the basis of isochrone age. And the similar lamprofire has been dated by Parazio et al. And they have found around 65.2, 65.2.
Same lamprofire they dated?
Yeah, more or less similar. So from the same locality.
Okay, you only supported in your paper 55 years in age of lamprofire.
Yes, but we think that should be rectified.
Yeah, but that gives support to our studies, paleomagnetic studies, although it is a relative dating. But yeah, we are trying to date it again.
Okay, sir.
But certainly it will come younger only.
Once again, thank to Dr. Ashish Dongre for his nice presentation. So thank you so much. And now I'll be handing over this mic to Professor Shukanto De for needful.
So the next talk is by Dr. Rashmi Rekha Naik on Lisi volcanics of Arunachal Himalayas. Want to stand here?
Yes, I can stand here. So good evening to all. Since morning we are watching presentation on Deccan traps, the Proterozoic magmatism in the southern part. Now I try to take you all to the Himalayas. A small patch of volcanics in the Himalayas, but a large impact of that. So my topic is insight on mantle plume heterogeneity through petrogeochemical characterization of lychee volcanics, Arunachal Himalayas. Actually, this is a work of GSI, and we have carried out a research program to link the ever volcanics, as you all know about the ever volcanics, and lychee volcanics, because there is a stratigraphic problem is also there, and the genesis part is also there, but in 2019, the dates of our volcanics came as 132, and that become related to the coagulant plume, and the Komei volcanics and the Ever volcanics, the Sylhet troughs, the Deccan troughs, all these are, sorry, not Deccan troughs, sorry, Rajmahal troughs and the Sylhet troughs, they all are correlated with the coagulant plume. While still the question is live for the lychee volcanics. So in my presentation, I will cover the introduction part, the distribution, because we should know where it is in the Himalayas, and the stratigraphic position of it, which till now we believe, and the variants of the lychee volcanics, its petrological characterization, and the mineral chemistry, geochemical character. And actually this item we have covered it in the COVID times, so very less data I have. Still, I try to make it interesting for you all. So as we know that the Earth is heterogeneous across all scale, being its composition or being its structure, and it took billions of years to achieve this heterogeneity, I can say. And this heterogeneity is achieved by the differentiation processes, mental convection, the plate recycling, partial melting, fractional crystallization, differentiation, magma mixing, all these things. And the most interesting rock type is the magmatic rocks, which records all these things. So lychee volcanics is one of them, which is correlated with the Abor of the Siang Valley, but in 1912, Brown referred it as a separate volcanic entity. And here the basalt, trachyandesite, trachyte are exposed, which are composed of alkali feldspar, phlogopite, plagioclase, apatite, ilmenite, and titanite. And I will try to correlate with these things with the metal heterogeneity. So this is the figure by the Garjanti, where you can see that these are the Panjal traps and these are the Abor volcanics, and this small patch is the lychee volcanics. Maximum of the volcanics are in the higher Himalayas, where the Abor volcanics in the Siang window and the lychee volcanics is in the lesser Himalayas. So this is the geological map, compiled geological map for the Arunachal Pradesh, where you can see this is the Abor volcanics, and here the lychee volcanics is there, which is associated with the Gondwanas. These are the Quaternaries, these are the Kimin, Suvarnasiri, Dafla, and here small patch of Gondwana is there, and the lychee volcanic is associated with this, and this is the Bomdila Nicis. So this is the larger scale, which during field work, because these are very glassy and very fine-grained rock type, so we classify these as the amygdaloid alkali basalt, porphyritic trachyte, amygdaloid alkali basalt dike, and the amygdaloid and porphyritic alkali basalts. This is the lychee village, and this road goes to the Kimin towards the North Lakhimpur of Assam, and this is toward the Zero Valley. So here you can see that these are the carved cell or carbonaceous cell of the Gondwana, where these are the lychee volcanics, and you see these are the amygdaloids and the glassy ground mass. So in field it is very difficult for us to classify it as a trachyandesite or andesite or phonolite or like that. So we use the chemical data for the classification. And this is the Gondwana. You can see the sandstone, carbonaceous cell sandstone sequence is there. This is the larger view of that here. And this is near to the MBT. So these are the rock types which exposed in that area, where you can see this as the amygdaloid part, and this is the porphyries of the feldspar. Here you can see a pink feldspar, that is the potash feldspar. This is a quartz trachyte, the class 3J, and dikes included this amygdaloid alkali basalts. These are some other variety where you can see that these are the very glassy, and the amygdaloids are there, and the porphyries are also there. This is lithic tube, weather one, and this is the genolith within the alkali basalts, and these are the dikes. Coming to the petrography, it is very interesting actually. The petrography is some of the answers till now I have not found actually. This is the glassy ground mass with the phenocryst of feldspar. Some are like skeletal feldspar are also there, and these are the interconnected amygdaloids are there with phenocryst. And here you can see that the ground mass has a spherulitic texture, and some part the feldspar, the biotite or the phlogopite are the internuclear place. And the ferruginous material are in some parts these make the interstitial spaces. Here also you can see that these are the ferruginous material which entered the melt, and maybe these ferruginous material are cooler than this one. So these are forming because of the surface tension, they make form like these bleb types. And this is from the lithic, the crystal tube, where you can see the lithic fragments are also there, and the phlogopites are there, and the crystal are there. And this is from the dike. When we collect the sample from the dike, that time we thought that it will be a glassy material and we will not see anything, but lots of materials are there. Here you can see the lithic fragments are there, and the crystal, the phenocrysts are also there, and the ground mass is full of potassic material and the phlogopite mica and ilmenite and rutiles. Cross pillars. But sir, in PPL also it's look like that only. Yes, yes. In the second photograph, I try to show those phenocrysts which we get in these rocks. So these are the potash feldspar, and ground mass is also full of potash feldspar. Here the glomeruloporphyritic texture you can see, and here the CPX are reserved, and here the phlogopite is also reserved with the potassic material. Here the phlogopite is oxidized and the ilmenite rims is there, and all these are the potassic material or the potash feldspar. Here we can see one xenolith type which contain the CPX and the inner material is potash feldspar, and here this is actually altered or the replaced. So here this may be pseudoleucite or part of any other mineral, but now this is altered, replaced by quartz, and the ground mass here potash feldspar. This calcite, actually first I thought that this is a part of the amygdules, but later we see that some apatite and these opaque minerals are there, and within this also small mica minerals are also there. So this could be a part of the mental genolith or from the carbonatite part mixed with this one. So when we carried out the mineral chemistry or EPMA analysis of this, you can see this albitic. Maybe earlier this may be a plagioclase CA rich, but now it is albitic, and the Na% you can see it is 99%, where the ground mass is potassic, which reserve this one, and the ground mass is 97% to 98% potassic material is there, and this is the thin section photographs of this one, and this feldspar have the less 81 to 83 in the core part and 64 to 81 in the rim part, the potassic one. And the ground mass is 96 to 97%. So the ground mass is more potassic than the phenocryst. And here you will see that this phlogopite, which I have shown earlier, the photomicrographs, reserved one, have the XMG at 73 to 80, and these are TIE rich one. And this is the part of the dike, which I have shown that this content that many materials that like the genoliths are there and the crystals are there. This show a immiscibility texture also, where you can see the potash feldspar is rimmed by the ilmenite or the iron oxide, and the quartz material, the silica material is there. So maybe this magma mixing type features is there. Coming to mineral chemistry, when we all the ground mass and the phenocryst are clustered in this part, in the potash feldspar part, only one albetic data we have, and most of the pyroxenes are in the dioxide, towards dioxide, some are in the augite field, and one azurine also we get over here. And the phlogopite is, the biotite is Mg biotite and the Fe biotite. coming to geochemistry, if you see that in the field we could not classify the rock type, so we took the help of the dash diagram, where you can see that it is ranged from the dacite andesite to teflon basanite. So you can see that trachyandesite and trachydacite, and in as these are the alteration is there, so we try to classify this with the help of the trace element ratio also, and these fall in the alkali basal and the andesite basal very well within the calc-alkaline series, and these are the sosoneric type. And if you here see the meta-aluminous to per-aluminous, it is not per-alkaline, so alumina is there. So seeing this, the multivariant diagram, you can see that the some are showing the negative correlation, the MgO, the CaO, the Fe2, FeO, and these show that crustal fractionation is there. But some are TiO2, this L2O3, Na2O, and K2O, and these are showing the partial melting trend, where the P2O5 is little bit fractionation is there. So when we plot this in the RE contact diagram, all these materials are showing the parallel trend, and the LA/YB ratio is 26 to 64. So there is a fractionation, and which show that a very little partial melting taken place, so that the LRE is very enriched over here. And in this diagram, the THYB and NBYB diagram, it show a little bit cluster contamination, and some are falling in the MORB OIB array. Here also it show a OIB trend. So here it is very much clumsy. So I took the advantage of this different type of from the same diagram, but the primitive mental diagram of the trace element. Here you can see that SR depletion is there, and some are showing the NBTA. NB depletion in some places is there. Here also it's NB depletion is there, but some are not showing any depletion in NBTA. So it suggests that there is a mixing of the material within the mantle plume, and all the samples are falling within plate volcanism. So if when we go for the petrogenesis part of this this trachyandesite and alkali basalt, this is a model for the earth. The mechanism took place within the earth, where we can see these are the mantle plume, super mantle plume. We can say these are the core mantle boundary, and from where the material is coming on. And this I would like to discuss some more, because this is where the Zhang et al. In 2019 they have published by taking those which are proved, like Morganian plume, the super plume, and the Anderson plume, and they have plotted these things. In the test diagram, only two diagrams I have taken one to compare with my my volcanics, to compare it to my volcanics, and my volcanics are falling in this part, and only 2-3 samples in the andesite and dacite part, otherwise in this part. So that may be a part of the super plume, where the mental metasymmetrism may be taken place due to the D layer, and in different places or different zone, or the different storage houses, the contamination or the assimilation of the subducted slab may be there. That's where they form the variety of the rock. So these are the conclusions from my study. Thank you.
Thank you, Dr. Naik.
Yes.
Now the questions from the audience.
Thank you, Reshmi Rekha ma'am, for your nice presentation. I have a small question. Have you gone through the paper on the same area by Nitu Mani Sharma and all these
Yes,
things?
sir.
So my simple question is that in which way your interpretation is differing from their version? Thank you.
Actually, sir, their interpretation is also like that, because they are also saying that the fractional crystallization and partial melting and assimilation is there. And the second paper by the Basumatraj, only 2 papers is there on the Lychee volcanics, one by Nitumani Sharma and one by the Basumatraj in 2024. Both are there saying that these are from the partial melting, and because phlogopites is there and potassic material is there. So from where the potassic material will come? So they are saying that the assimilation is there. There must be assimilation of the subducted slab in the mantle plume. But the variety we are getting the variety we are getting from the phonolytic to the dacitic to the trachyandesite. This shows that this is the part of the superplume. Now the question is that should we correlate it with the above volcanics, or is there any separate small plume is there from the D layer? So that is the question that we have to solve, because here it is associated with the Gondwana which are Permian, and the above volcanics which are related to the Kerguelen plume or the Rajmahal trap or the Sylhet traps, those are up to Cretaceous, that is 132. So how much we extend the age of the plume to correlate this Permian volcanism with the Kerguelen plume? That is the question, sir. Cretaceous, sir, 132 age. From Wadia Institute, Singh, sir, they have dated that one.
Okay, one more question we can take. If not, thank you. It was a very nice presentation.
Okay,
The next talk by Dr. Payal De on PGE mineralization of Khandwa basalt.
Can you tell me this? It's a pointer, and this is the forward and backward. Okay. Hello everyone, I am Payal De. Recently I am working as a postdoctoral student at IISER Beherampur, and today I am going to present the research output of our experimental studies related to the assessment of PG potentiality of Khandwa basalt from Eastern Deccan Volcanic Province in the light of black shell contamination. Now, basalt is naturally not a very good reservoir for PG mineralization, as it forms due to partial melting of about 15 to 18% of the parent mantle, and for PG mineralization, sulfur is very important. And according to Momi et al. 2003 and 2006, if the partial melting of the mantle exceeds by 30%, the sulfur present in the mantle comes into the melt. And for basalt, it is only 15 to 18%. So basalt is not a good reservoir for PG mineralization. But if the basalt interacts with some sulfur-rich sediments, the potentiality of the PGE mineralization increases. Now, this type of experimental work has been done by Deegan et al. 2022, Patton et al. And Vitonen et al. 2012. They have done this kind of experimental studies where they have contaminated different LIP samples or Duluth complex samples like Canadian high Arctic LIP samples with different contaminants to check the potentiality of the PGE mineralization of those LIP samples. For Deccan, this kind of experimental work is rare. So considering that, we have tried to run few experimental study. We have on one at 1 atmospheric pressure, where we have contaminated the Khandwa basalt with pyratiferous black shell contaminant from Vindhyan supergroup. Now, Deccan is a very extensively studied LIP of almost 5 lakh square kilometer and reaching up to a thickness of 300 meter, and it is considered that the basement of Deccan volcanic province is the pre-existing gneissic complex or Gondwana sediments, and Vindhyan supergroup sediments are also present beneath the Deccan volcanic province. There is a well-established chemostratigraphy for the western part of Deccan volcanic province. Now, this is the geological map that we have prepared of our study area, and here we have identified 3 different lava flows with two dike rocks, and intertrap beds are present in between the flows. From particularly this area, we have taken the sample for our study. This basalt is from the lower colonnade zone of the lowermost flow of this area, and we have contaminated this sample with a pyritifera black shell sample, which we have collected from the Amjor pyrite mines area of Rohtas district of Bihar, which is a part of Bijoygarh formation of Vindhyan supergroup. Now, these are few photomicrographs and field photographs. The uppermost photomicrographs is representing the basalt sample, and the photograph B is showing the field occurrence of the pyritiferous black shell, and C is representing the photomicrograph of the same black shell. Now, these are the laboratory methods that we have followed to prepare 3 different whole rock contaminated samples, where RP1, the first table is showing the details of the samples. RP1 represents 10% black shell contamination. Similarly, RP2 and RP3 is representing 15 and 20% black shell contamination. This next table is showing the exact duration and the temperature of the different experimental runs and to which these samples were subjected to. And after the experiment was done, we have collected the resulting glass, homogenized it and sent it to NGRI for the analysis. When the result came, it showed that these oxides, SiO2 and K2O, is increasing with increasing degree of contamination, but CaO is decreasing. Now, these diagram represents the behavior of the different PGE elements like palladium, platinum, Cu. Cu is closely related to PGE, and lanthanum. Palladium and platinum is showing similar behavior, where they are increasing with increasing degree of contaminant. Their concentration is increasing respect to the parent melt, but Cu is decreasing, and the change in lanthanum concentration is negligible. Next, in this diagram also, the PG elements are showing increase in concentration with respect to the parent melt, with increasing degree of contamination. Even the ratio PD by IR is also PD by IR ratio is decreasing, which means IR is increasing much more than the PD. Now here, this table is the summary table where I have summarized all the element-wise enrichment. These are showing the maximum enrichment of different PGE elements compared to the parent basalt melt. And this diagram is showing the interrelation between the PGE elements with the light rare earth elements, where if we consider PD, with respect to PD, Cu and La is the enrichment in Cu and La is negligible. But in case of platinum is increasing much more than the PT. When platinum is in almost 1 lakh ppb in the contaminated melt, Pb is around 2200 ppbs. Now, here to present the data in a systematic manner, we have calculated the parent basalt normalized calculation, and here we have presented that in this table for all the contaminated melts. And this diagram shows the pictorial description of that data. Each bars here, it represents the highest contamination, the highest concentration of different elements, but the color code shows the percentage of contamination at which the elements have reached that highest concentration. We can see that different elements are achieving that highest concentration not with increasing percentage of contamination. Some of the elements are reaching that highest concentration at the highest percentage, and some of them are achieving that even at the lowest percentage of contamination. So from this study we can conclude that contamination with the pyritiferous black shell is definitely increasing the PGE budget of the basalt, but it is the element wise increase of the concentration is not uniformly depending on the percentage of contaminant, and because of this contamination, because of sulfide oversaturation, sulfide droplets may form in the contaminated melt, which may in turn give rise to PGE mineralization. So these are few selected references which I have used in this presentation, and that is all. Thank you, sir, for listening. Sir?
Why you have not analyzed for PG or any of the elements? Exclusively basalt and exclusively black shale. Obviously,
we have
PG is coming from black shale.
Yes, yes.
So then what is that you want to prove?
Sir, actually we have tried to get a glimpse if the Deccan basalt have somehow got an interaction with the Vindhyan. Yes, if it had happened, this might be the situation.
A very interesting work indeed.
Very nice. Nicely explained.
Same thing here. When you contaminate a basalt with a shale, forget the PG. There is one thing that you can expect, and that is the melt will move from a gabbroic to more of a noritic composition. What will happen is that instead of clinopyroxene, orthopyroxene will begin to precipitate, and the plagioclase will become more calcic. That is what will be the outcome of assimilation of a shale. If a basalt assimilates a shale. Is something like that seen in those basalts?
Actually, we haven't done any mineral chemistry for this sample, run product samples. We have got the glass, we have homogenized it in powder form, and we have done the analysis on it for whole rock. We have not done any mineral phase.
No, but what I'm saying is you are checking something which may have happened.
May have happened.
So I'm saying that in the original Deccan where you suspect this may have happened, is there any report of any orthopyroxene crystallizing from the magma? That would be a neat check actually. So you can try it out. And where did you do the experiments?
In our lab, we have.
In ISR Berhampur?
No, sir.
Then?
In University of Calcutta.
In Calcutta University. It's a very good thing you've tried. But this, I think you can just try this and see if that is the case.
Whether there is any report for it. Yes. In Calcutta, I have done this work. Sir.
I have just one observation here. So, I think if you are talking about PG mineralization, generally you have also introduced that it should be with sulfides. Huh? So the question is that you have basalt powdered, shale powdered, mixed, melted. Now your PG is within the glass, in the melt. It is not with sulfide.
It is not with sulfide.
So how you can use this result to mineralization in the natural rock sinks.
Sir,
No, I think black shells have sulfides. So they must be contributing it, definitely. That's what Dr. Balram has asked. Before that, you should analyze your basalt and shells.
we have
Mention-
done
you
that, sir. We have done that,
Have
sir.
done.
Yes.
After you contaminate, here the contamination means that you mix and then melt experimentally. Now the experimental melt product is only male, and that male you do not know whether sulfide
Right.
is crystallized
True,
or
true,
not.
true.
And in that sulfide where this platinoid group
Sir, here we are assuming that as fractional crystallization plays a role in case of Deccan basalts, it may have happened that from the sulfur liquids which have formed. No, no, no.
You are a glass.
one temperature and you
That's
drop
it. Glass. And another
We have quenched.
homogeneous. It's a melt only. It's
Yes,
a
sir.
solidified melt.
We should
That's
have
it.
done that.
It's a frozen melt, say
That's
glass.
it. No, Shaibal, to you answer your question, I recall a paper by Chandrasekharam and Seth. They have reported OPX from Deccan basalt contaminated with shale or something, APS, long back, 25 years ago. Yeah. Yeah? Something.
that will take place in a plutonic condition where you have that interaction with in this kind of.
Yeah, one more.
I did not understand the logic of the experimental procedure which you followed. Your aim was to study the solubility of black shale in basaltic magma. But what you did really was to artificially mix basalt powder with shale powder.
At
And
one
then you took it to
atmospheric
the melting
pressure.
temperature.
Yes, yes.
So what does that prove? It does not prove what you wanted to show us. What is the solubility of? Because you just took it to the temperature which was required. You mixed the powders. You did not have a basaltic liquid in which you put black shale and measured how much was dissolved. So this logic has escaped me. Okay?
Sir, sir, are you saying that if we used some pressure with it, it would have been?
No, nothing about pressure. Nothing about pressure. You have created an artificial mixture, taken it to the melting point, so it was neither a basalt nor a black shale. But that is not the same as a contaminated basaltic liquid, because you did that artificially. You can take 90 of shale and 10 of basalt powder
Yes, sir.
and melt it. Okay? Will it mean that basalt is able to dissolve 90% by mass of shale? No.
Actually, we have tried to do more percentage of black shell contamination, but beyond 20%, it didn't digest the contaminant.
Yeah, but see, you can't mix the two powders of two rocks and then take them to the melting point and say anything, because what you need is a basalt which is at the liquidus or superheated, and then you add your shale, whatever contaminant you want to add, and there is some way to measure what is the degree of assimilation. That would prove what you were trying to show. Okay, so I am not convinced that you showed assimilation of shale with this experiment, but maybe I did not understand.
No,
you
no,
can clarify to us or think about it.
Yeah.
Thank you.
So that work generated a lot of interest. So one of the question is that whether it is actually mimicking the real situation or not. Yeah, that is one suggestion. You
Yes,
can think about that.
I need that.
That you add shale solid and see how much of it dissolves. That probably would be a better thing to do.
Okay.
That's what Professor Shen was saying.
Okay.
So because not all of it will melt.
Okay.
Only the part which is melting will actually get
We assimilated. Okay. Okay, sir.
Okay, yeah. Okay, now it is the time. Devalda. It's the time. So big hand.
Thank you.
Good work. Okay.
Thank you, sir.
So I thank all the speakers for their presentation. Now I hand over to Sneha probably.
Thank you, Professor J. Ray and Professor Shukanto De. And now I will request our director to hand over the memento to our chairperson. With this, we have completed our technical session for today. So now next session is the poster session chaired by Dr. Amiya Kumar Samal, Dr. Rohit Pandey, Dr. Shimantini Sen Sharma, and Dr. S.N. Mahapatra. Poster is already displayed in the downstairs. And after that poster session will be completed by 7:30, and after that poster session, that all the certificates will be distributed for all the presenters for the talk and for posters. Both the certificates will be presented near our selfie point today only after 7:30. Before dinner, yeah. And dinner will be started from 8 p.m.